Learn PyTorch and PyTorch Syntax. This course walks through 5 hands-on exercises designed to help you understand and apply PyTorch syntax in real-world tasks. It starts with tabular data classification, then moves on to image classification using both custom and pre-trained models. You'll also explore audio classification and text classification using BERT, giving you a well-rounded introduction to PyTorch's capabilities. Omar developed this course.
Hello and welcome back to this series. In this series, we'll be practicing multiple PyTorch exercises. The goal of this series is to get used to PyTorch syntax since it's a bit complicated. Not complicated, but it requires more work to do than TensorFlow. So what we'll be doing here is, this is the first exercise. So what we'll be doing here is the rise type classification. It will be a tabular classification. We'll use a CSV file to do a classification with PyTorch. Later in this playlist, we'll be dealing with images, text, and even more complex exercises such as image captioning or large language models. But for now, we'll start by the rise type classification or the table classification, just to know if it's, just to get used to the PyTorch syntax, and we'll be going into more difficult exercises in the later videos gradually. So the first thing, we'll be using the rise type classification dataset. The dataset is from Kaggle. It's an open source dataset. I'll attach the link in the description. You can find explanation about the dataset here. So we have it's a binary classification dataset, which means that we have either the rise based on some features. It's either Jasmine or Gonin, which is 1 or 0. So I believe maybe this is something related to good or bad quality or something like that. But anyway, we have here are the attributes or the features, which are the ID, area, major axis length, minor axis length, eccentricity, convex area, equiv diameter, and multiple other things together with the class at the end. Before we start coding, we know that ID is something that we need to remove. It's just a number that is assigned to each entry, and usually IDs are being removed from the process of machine learning because they are not representing anything. So it's just a number assigned to one entry. And here is the dataset. So let's go and download the dataset with the same way we have done inside the video that we introduced how to get dataset using Colab. So we'll be installing pip install open datasets -- which means doesn't print the installation process. It does the installation in a silent process, let's say. And then we'll go into import open datasets as OD, and OD download the rise type classification dataset, which is just the link from Kaggle. So let's start downloading it. Let's make sure first that we are connected into T4 GPU. Usually, of course, machine learning or deep learning things using TensorFlow or PyTorch, better to use better to use GPUs, because the process will be much faster. The training process is much faster with the GPUs. I know this is a tabular problem, CSV file, and not a very huge file, not to be used for deep learning. So GPU may not be a huge deal here, not very important thing here. So, but it's always recommended that you go into the GPU. Okay, so now I provided my username and the Kaggle key. So we had a detailed video about this process. I'll attach it in the description as well, if you want to know more about how we install or how we download each dataset from Kaggle into Google Colab directly. Okay, great. Now in the next cell, we will do our imports. Okay, so let's start by doing our imports. We'll start by importing PyTorch main library, which is Torch, and we will also be importing the NN class from PyTorch library as NN, which means that we are getting torch.nn and giving it such like a nickname or something that we can use instead of writing torch.nn. So we'll use only nn, stands for neural network, and this one will have all the layers that we are going to use. The linear layer, or the equivalent to the dense layer, the convolution, if you want to use any, the LSTM or the long short-term memory, the recurrent neural networks, any layers will be in torch.nn, okay? Then we will be getting the Adam optimizer from torch.optim import Adam, we're gonna use, Adam optimizer, and then we will be using also the data set and data loaders object. We will know more about this shortly. From torch.utils.data import dataset and data loader. Then we will don't panic from these imports. Maybe some of them you are not aware about, but it's okay. We will learn each one, the usage of each one later. From torch summary import summary. Okay, this one is to print the model summary, or how the model architecture will be at the end. Also, we will import from sklearn.model selection. We will import from this one a train test split. Okay, and also from sklearn.metrics import accuracy score. Now, this is a binary classification problem, so accuracy would be efficient here, would be enough. But if it is a multi-class problem, it's strongly recommended that you use precision and recall, as it will be easier to monitor the exact problem of the accuracy. Import matplotlib.pyplot as plt. Okay, so why we are going to need this? We are going to need this because we want to plot the training progress that we will be doing. And then we will import pandas as pd and import numpy as mp. I don't remember that we will be using numpy, but just let's keep it just in case. Now, next thing is that you have to know that PyTorch does not automatically detect the GPU, okay? So you have to specify it automatically. Unlike TensorFlow can detect the GPU automatically, but PyTorch unfortunately cannot. So what you have to do is to tell PyTorch that you have a GPU, you have a CUDA GPU. Okay, so we are using Google Colab here, so it's by default, of course, it's CUDA when you choose from runtime. If you choose that one, it's CUDA. This is a Tesla T4 GPU from NVIDIA. This is the CPU. This is Tensor Point. And these ones are available for Google Colab Pro. So you don't need these. We're gonna use the free ones. The free one, device equal CUDA. So you are telling it the device is CUDA if torch.cuda.is underscore available. Okay, else CPU. So what I'm doing here, I'm assigning a variable called device. Device is CUDA only if torch.cuda.is available is true. So this function is a function that is built in PyTorch. You can go and search for it in the documentation. The function gives true if a GPU is found, and gives false if GPU is not found. So what I'm doing here is that I'm assigning CUDA if this function is true, else I'm assigning CPU. And now let's blend. Device is, let's wait for the imports, CPU. So we don't have a CUDA device available. Let's go and make sure that it's not detected yet. Let's try to run again. Sometimes this happens. Okay, connecting. Yes, now we should run again. And let's give it a moment. Yes, now it's CUDA. So now it was able to detect the GPU. Since this one I already changed before the start of the video, but I think I didn't save. So it's a normal thing that could happen, no worries. Just make sure that the runtime is T4. Okay. Of course, other problems could be that PyTorch was not installed correctly, but we will not go into this. Okay. If you followed the exact description in PyTorch documentation on how to install it, everything will be fine. Also, if you are using Google Colab, no need to install the PyTorch. It's already installed for you. Okay, great. Now we will need to work on our data. So let's start by reading our data set. Data df equal pd.read_csv. And let's get the exact path of the data. So we're going to refresh here. Okay, so we need to run this again. Okay, that's my fault because we changed the kernel, we changed the runtime, so we need to run this again. Okay, no problem. Now, when we run this, okay, let me check. And yes, we are good. So here, rise type classification, CSV file, we are going to take path of that file and we are going to use it here. And then we will check the data just by printing the data.df, just by printing the first 5 rows. Okay, and here we go. So the data is here, looks good. Okay, so now what we will be doing next is that we will do some basic pre-processing. We are not going to do some like a huge pre-processing, because this is not the goal of this series. We will have another videos. I'll upload another videos on how to pre-process the data to achieve better accuracy. But for now, the goal is to get used to the PyTorch syntax and learn how to use PyTorch syntax properly. Okay, so we will be just dropping the missing values, although I don't think there is any, but let's see. In place equal true. So this line drops any missing values. And also we need to drop the ID column, since we mentioned before that ID column is not necessary, okay, is not important in the machine learning, okay? So dot drop like that, and we will write the ID here, and we will mention axis equal 1, which means that it's a column, not a row. Axis equal 1 means that it's a column. In place equal true. Okay, so this is the first step. Let's print the data shape as well. Data.shape after doing these pre-processing things. So let's data is not defined. Data df. Okay, data frame. So you can see that ID is not found in axis before because we removed it before, and this line gave an error. So okay, no problem. We can run this again. We read it and we can run this again. Now we are good. Okay, so we have 18,000, more than 18,000 row and 11 column. Okay, so we can also print data.df head again to see the data. And perfect, we don't have the ID. Okay, just to make sure that we are good. And now let's print the output possibilities. What are the outputs that we are having? So we are expecting 0 and 1 from the data set, but let's also print them if you want. Data underscore df of class dot unique, which will print these values for you, 1 and 0. Also, you can print, if you want, you can print as well the frequency of these values. So it's dot value count, I think. Dot value counts. Okay, so let's see. Yes, perfect. So we have the class 1 is around 10,000, almost 10,000 row, and the other class 0 is 8,200. This data set is not perfectly balanced, but the gap is not that big, so we can proceed. Okay. There are some techniques, of course, that you can handle the unbalanced data set, but it's not the scope of this lecture. Now, let's do the pre-processing, another important part inside the pre-processing, which is the normalization. Why we want to do normalization? So you can see here that the values are extremely huge, okay? This is not a good thing, okay? Usually we want the values to be small because the weights of the neural network are relatively small compared to these values. Also, when the weights are being multiplied by the inputs throughout the different layers of the neural network, these values are becoming very, very huge, which means that it will be computationally expensive, slower, and as well, sometimes when you are using the loss function to calculate the loss or the error, it may round up the values, okay? Because the values are very big, so it may round up the values. So it's better that we normalize these values. And by normalize, we mean each column, the maximum value of each column will be 1. So how we're going to do this? We are going to take each column, all the values in each column, and divide it by the largest value in that column. By this, we have the largest value will be 1. Okay? And we won't, we will not lose anything in the data because we will be doing this on all the data. Okay? Okay, great. Now, first, let's have original underscore data frame equal data underscore df dot copy. Why we are doing this? I'll tell you. We are taking a copy from the data frame that we have, and we are having it in a variable called original data frame. Why? Because we will need the original values or the old values for the inference, okay, when we do the final inference after we finish all the exercise. Now let's not get into that now, and we can proceed, and at the end you will know why we did that exactly. Okay, you will see why this is important. Now let's get for column in data underscore df dot columns. Okay, so we are going through each column inside the data set, and then we are taking data underscore data frame of that column. So this column is equal to data underscore df of that column, divide by what? We said the largest value in that column. Then data underscore df of that column dot maximum. Okay? It's also better that you add absolute value dot abs, but it's not important really because these values doesn't seem to have any negative values, but we can keep it just in case, because of course we cannot see all the 18,000 row, but I don't think there is any negative values, of course, because this is something obvious according to the purpose of this data set, but let's keep it like that if you want. Okay, and then we are going to view the new data frame. Okay, now let's see the result, and here we go. So you see the difference between the values. This is 92, now this is changed, this is 64, this is changed. All of them are divided by the largest column, by the largest row, by the largest value in each column. Okay, okay, perfect. Now let's get into splitting our data set. Okay, up till now we didn't touch PyTorch yet. All of this is just dealing with the data. Okay, so we'll have x, which is the inputs. You can call it inputs, but let's keep x for now, equal numpy array, np.array of, so we're gonna convert it to numpy array of the data frame dot iloc, okay, colon, comma, colon till -1. Okay, what does this mean? This is actually, you are taking data frame, our data frame, you are taking all the iloc means take specific part of the data frame. So we are taking all the rows and we are taking all the columns except the last one. This means that, okay, this colon -1 means except the last one. Now, because we know, of course, that the class value is the last one, so we are not taking it as an input. Now we will do almost the same with y. Okay, I copied it. Let me show you how. We are going to take all columns as all rows as well, but we are only going to take the last one. So we'll remove this column. Okay. This means, so basically, this means all until. You can think about it like that. And this means only that one. Okay, so colon means all except the last one. Okay, okay, perfect. Now you can run this one. Okay, we are good. Now, what we will do is to do splitting. Now we need to split the data set into training, validation, and testing. So, you know, training data is for the training or for the model to learn. Validation is to validate the model during the training and monitor its progress. It's the data that is the model is tested on during training. And testing data is the final testing after the model has done all the training. Okay, now let's xtrain. Let's define xtrain, comma xtest, comma ytrain, comma ytest is equal to what? Equal to train test split, and we are going to take x as the inputs and y as the outputs, and we will define the test size of our data is sorry, there is a typo here. Test size is 0.3, which means that 70% split. We are going to split the data into training 70% and testing 70%. By default, this function returns 4 values. Great. And then we can do the same, okay, for validation. So let me show you. Let's copy this one. And first, we will need xtest here. This is going to be xtest and ytest. And this one will be x validation and y validation, okay? And then we will be doing, we will be taking the x, we will split the x test. So the goal of our, the goal of this split is to have 70% training, 15 testing, 15 validation, 15 testing. Great. So since we split already the first one for training, we will split the next one for from testing. So we split the original data into training and testing. We will take the testing, which is 30%, we'll split it by 50%. So we will take the x test and y test. Okay, cool. Now let's run. Okay, great. Now we can check the shapes of the data, xtrain dot shape, and we can print it. Let's print xtrain.shape, and let's as well print xtest and x validation. Okay, and great. So now we have, this is 70% of our whole data. This is 50-50. Sorry, this is 15-15, which adds up both to 30%. Okay, great. Now, I wanted to add one thing, that we have a repo that is containing all the details about all this lab inside a GitHub repo that is already uploaded on GitHub and having a very detailed explanation of all what I'm doing now. Okay, so you can go through it if you feel that anything is confusing. Okay, now comes the interesting part. Okay, we will be using a dataset object. We will create a dataset object. Okay, why we want to do that? First of all, PyTorch, think of it as a huge ecosystem that has a lot of functions, a lot of classes that can work together in a very seamless way. Okay? Okay, great. Now, how PyTorch understands the data, how PyTorch see the data. It doesn't see it as a pandas. Now the data is pandas or a NumPy array. This is different objects, but we want a data set, a PyTorch dataset object. Okay, so we need to convert our data into PyTorch dataset object, but we need to specify the details of our dataset or how to access the dataset. Okay, okay. Now this is not complicated. Okay. Let's follow, let's start and you will see what I want to do. Okay, now we will create a class. The class is called dataset, and the class inherits the dataset object that we imported above, this one. Okay, this is a class. Okay, it's not something it's not a file or something. This is a whole class by itself. Okay, now the class is having multiple functions. Okay, we will take the functions inside this class and we will overwrite or modify some of these functions, okay? So to match the properties of our data, okay? So what we are going to do exactly here is def underscore underscore init. We will define our constructor that takes self. What else it will take? It will take the inputs and the outputs. Of course, this is totally customizable. If you want to change or play with that, feel free to do so, okay? And x comma y. So this is taking two things, okay? This is taking the inputs and the outputs. Great. Now we will have self dot x equal torch dot tensor of what? Of x comma d type equal torch. I'll explain all of this, don't panic, okay, because I know that this syntax may be a bit complicated. Dot to device. Okay, what did I do here? Okay, this whole thing that seems complex is not complex at all. We defined the self.x, which means the x or the input value of that dataset object will be the x that we got from the constructor, and this is fine. Now the x we got from the constructor is maybe numpy array, maybe a normal list, maybe a pandas, so we need to convert it to torch tensor. So torch understands the tensors. If you want to deal with PyTorch, you need to have your data as a tensors. So inside this dataset object you have an inputs of called x. X is converted to torch.tensor. Torch.tensor is something like a list. What will be inside this list? A list or a vector or a matrix, but for now it's let's say it's a vector, okay, because it's one dimension. Now how do we know it's one dimension? You can see that this is all the inputs are one dimension. It's not an image or a video or something. And d type is torch.float32, which means that it's a float 32 type. And the last part is moving this value to device, which means that we move this list to device. What is device? Device is the GPU, the CUDA device that we defined before. Great. Now we're going to do the same, exactly the same, but with y. So we are going to define here y and here y. Okay? Okay, perfect. Now that's it. That's it for our constructor. Let's go into the next function. We have two functions that we need to modify from the dataset object. Not going to very deep details, but these functions will be used inside the training and how the model will be training. So pay attention to them, okay? The first function is called def underscore underscore len underscore underscore self. Okay. Now I am not naming this function as whatever I want, okay? Because as we mentioned before, the function is already defined and already built inside PyTorch, but we need to modify it to match our dataset and to be suitable for our dataset. So we will do def len. We are going to return the length of self.x. So what does it do? This function basically returns how, like the shape of the input, okay? Okay, great. Now, def, again, I'm saying these functions can be customizable on your own, okay? But you have to understand what you're doing. Okay, now the next one is def get item. In the same way, it is written like that. I'm not doing it on my own. This is something that you have. This is something from PyTorch. Get item means that we want to get a specific item according to the index. So it takes as well index. Okay. So maybe we need item, like in this table, we need item number 3. So we have to output all these values and the output. Okay. We need the full item. Okay. So we need all of them. So what will we do? We are going to return self.x of index, comma self.y of index. Okay, and that's it. Now we have our class ready. We need to create objects for training, validation, and testing. So let's create them. Let's create them in the next cell so that you don't get confused. Okay, perfect. Now, no problems. Now we create the training. Data will be dataset of x underscore x underscore train comma y underscore train. And we are going to do the same with the validation. Let's change the names, validation and testing. And we are going to give it here x underscore val and y underscore val. And then we are going to give here x underscore test and y underscore test. Okay, let's see if there is any problems, and looks good. Great. Okay, now we are done preparing our dataset object. We didn't get yet into the data loader. Okay, so let's start on the data loader now. Okay, so let's start with the concept of data loaders. Now, the data loader concept is an interesting concept. And the thing is that when you do the training loop, okay, the problem here is that a TensorFlow is hiding or doing a lot of things for us in the backend, and we don't see that. And that's why TensorFlow is a good thing for beginners. But let's think about how AI is being trained, how any machine learning model can be trained. So basically, you go through all the data, pass it through the model, and then calculate the weights, do the back propagation, and do all of these things. Okay, but when you go through all the data, how do you go through all the data? You don't go to the data one by one. You go by the batch size, right? Okay, then if we go by the batch size, we need to go into like groups or batches of the data, which means each batch is 8 or 6 or 4 or 16 or whatever you specify the batch size. So to go to the batch size of the data, you create a data loader. A data loader basically is an object that you use to do the for loop during each epoch to loop through a specific amount of batches. Okay? Okay, so let me declare 3 data loaders. So a data loader for each data set that we have. Training data, validation data, and testing data. So let's name train data loader equal data. Maybe if you don't understand it completely now, maybe you will understand it better when we start the training loop. Training underscore data, comma, batch size equal. Now let's specify the batch size as 8. You see here by default it's 1. Okay, so let's specify it as 8. Okay, you can specify it as whatever you want. Okay, and shuffle equal true. We have a lot of course, other function parameters, but we will only use these. Shuffle equal true means it shuffles the data or change the order of the data in terms to avoid biasing. Now let's do the same line for each data set. So we're gonna do validation, and here we are going to do testing data loader. Let's call this validation better. And we are going to put this here and that one here. Okay, perfect. Now we created our data loaders. Now, what is like, how still, if you don't understand completely the data loader, no issue. So let me show you one thing. So for let's say x comma y in train underscore data loader print x, and let's print like an equal signs and print y, then break. Okay, now what am I doing here? I am looping through the data loader. So you remember we specified the batch size is 8, right? Then which means that the data loader loops through 8 like values of, like, it loops through 8 data rows at once. Okay, so each time 8 data rows, next time the other 8 rows, next time other 8 rows, and so on. So when we loop here, we loop through x, which are the inputs, and y, which is the output, and inside the data loader. So here I printed x, And break, I'm just stopping at the first loop so that we don't get the screen full of numbers. Okay, so here you can see print x, it printed x, which means the first row, second row, third row, fourth row, fifth row, up until 8. And the device is CUDA 0, which because we transferred already them to device. And here we printed first label, second label, third label until 8, which means that if we change this to 4, okay, it means that we are looping through multiples of 4 for the data. Okay, like here, you can see 4 rows, 4 labels. You see? That's the purpose of the data loader. So we can keep it back 8, and we can continue our training loop. Okay? Okay, perfect. Now, what's next? After this process, we are going to build our own model. Okay? So we will build the model same way as we built the custom dataset. Okay? We have a model, and we will be doing the inheritance of the model. Okay? Okay, let's see. Class my model nn.module. Don't worry, we are going to explain these things. Now we are creating a class called myModel. It inherits from my nn.module, which means that it takes all the functions in nn.modules and all the properties in nn.modules, but we will modify the instructor, of course, the constructor, of course. And we will modify as well the forward function. This is really interesting. Okay, it may seem not to be very interesting now, but I will tell you why. I'll tell you when we reach to the forward function. Let's start by the init, the initialization or the constructor. Now we will write super my model, okay, comma self dot underscore init underscore brackets. This means what? This means that we will use the same constructor of the NN module. So here we created our own constructor from scratch, but here we will use the same constructor of NN module, but by using this super, and then we will create the layers. Let's create self.input underscore layer is equal what? Now we need to specify the input layer. Input layer is a normal linear layer. Now linear layer is like a dense layer or a normal multi-layer perceptron. Okay, multi-layer perceptron, one layer of multi-layer perceptron. Okay, x dot shape of 1. What does this mean? This means the number of columns of x, which means that the number of inputs, because the columns are the number of features, which here showing n features. This is the input features. What are the output features? The output features is the hidden neurons. Okay, so how many hidden neurons do you want in the next layer? So you think about it like that. It's something sequential, right? It's going one by one. So the input is how much? The input is 10 rows, 10 columns, and the output is going to how many neurons? Let's say 20 neurons. So this is the hidden neurons. Or maybe better for you that we write hidden neurons, and we define hidden neurons up as 10, let's say. Okay, and this is the input layer. Now the next one is self.linear, a normal multi-layer perceptron layer, or we can consider this as the hidden layer. Linear of hidden neurons. Let's wait for the, okay, hidden neurons, and the output of it is what? Is 1. Okay, don't forget we have only one output, which will be either one output layer, which will bring a probability either less than 0.5, which means 0, or greater than 0.5, which means 1, since it's a binary classification. So we need a activation function between 0 and 1 for binary classification. So self.sigmoid, and we are going to use nn.sigmoid function. You see here nn. I mentioned before that nn is, we use it whenever we want to use any layers or activation functions. Okay? Okay, great. Now we defined our layers. We know our layers. Okay, you can put much more linear layers. You can try dropout, you can try whatever, okay? But the thing is that now we need to specify the forward propagation. What does it mean? In this function, we need to specify how the data flows inside the model, okay? How the data goes inside the model. Okay, so the data starts by, the data is x, represented x, and x is equal to self.input underscore layer of x, which means that first it goes to the input layer, and then x, the new x we got is self.linear x, and then x is equal to self.sigmoid of x. And then we are going to return x, okay? So what did we do here? We created the flow of the data. So first, the data will go to input x, to the input layer. The x will go to the input layer, and then the output of that input layer will go to the linear layer, and then the output will go to the sigmoid layer, and then we're gonna have the final output. Now this is a straightforward flow. It's a normal flow of the data inside the model, forward propagation. But this is interesting when you want to build a completely custom model. You can play completely and modify completely how the data flows inside this model, okay? Okay, great. Now let's create our model. So let's write model equal my model, okay? And we should move it to device. Now, don't forget, everything you're creating in PyTorch, you need to move it to CUDA device, okay? Or whatever device you have. By the way, you can put here MPS if you have a Mac and you set up using Mac Silicon processors, okay? Okay, now we moved the model to device. Let's run this and see. Okay, everything seems good. Now let's create the summary, okay? You remember we used torch summary. So here we can use this function to see the data, to see how the model will look like in a very user-friendly way. So let's try it. Summary of model, comma, x dot shape of 1, comma. Okay, now let's see that. Great, it's working. Now do you see that? Okay, we have 121 parameters. Okay, let's get to know our function better. This function is called summary. So the function takes the model and takes an input, the input shape. The function in the back end does something like it imagines how the input is, and then imagines a back propagation, sorry, a forward propagation to see the output shape of each layer and to see the type of each layer it's going through, the number of parameters, gives you more details. In TensorFlow, we have something like this. It's called model.summary, I believe. I'm not 100% sure, but I think it's model.summary. But you don't need to specify the shape of the input. But here, unfortunately, you have to specify the shape of the input. As we said before, PyTorch needs you to do a lot of work. It's not difficult if you understand the problem, or not the problem, if you understand how machine learning works. It's not a big deal, but you just need to get to know the syntax. Okay, great. Now we have the layers. So layer 1, layer 2, sigmoid, and the output shape is 10 by -1. Why -1 here? -1 here represents the batch size. When we use more data, we will use by batches. So we will use 10 columns, 8 rows, because we'll use a batch of 8. So here it's represented by -1 because it's just a one instance, okay? It's a one row only. And 10, then linear is getting 1, which means that it's getting one output and goes to the sigmoid and gets the final output. Total parameters is 121, trainable parameters is 121, non-trainable parameters is 0. We'll understand these later in the later videos, not for now. And this is the size of the model. Okay, looks good. Now, what's next? Next is that let's create the loss and the optimizer. So the loss function is usually criterion. Okay, it's referred to criterion in most of the references. So nn dot BCE loss. Okay, I think that's the correct way. Yeah. Okay, now the next one is optimizer is Adam. Okay, now first the loss criteria is nn.bce loss. BCE loss is binary cross entropy loss. Okay, and the optimizer we are going to use Adam. Now we need to tell the optimizers that you will be dealing with that model. So we need to give it model.parameters, which means that we are giving it the weights of the model that this optimizer needs to work on. And also we'll be giving it the learning rate, which let's say 1e minus 4 or minus 3, okay? And that's it. Now we created the loss and the optimizer, and both works fine. Okay, cool. Now let's start the training function now. We are going now into the interesting part. So first of all, in the training, we need to have 4 lists. A list for the total loss of the training throughout the training epochs, the total loss through each training epoch, the total loss through each epoch but for validation, and the total accuracy for training and the total accuracy for validation. Why do we need this? We need to record this after each epoch, and then we can plot them and see if the model is overfitted or not. Okay. Total underscore loss underscore train underscore plot. This is a list for training, and we're gonna have total underscore loss underscore validation underscore plot. And then we will have total underscore accuracy underscore train underscore plot. And then we're gonna have total underscore accuracy underscore validation underscore plot. These are empty lists that will be filled inside inside the training loop. Now for epoch in range of epochs. Now for each epoch in range of epochs. Now we didn't define epochs, so let's write 10 instead of defining, or let me to make it easier for you, we can write here epochs equal 10, so that you know what is 10 exactly. And then we can total underscore accuracy underscore train equals 0. I'm going to tell you each what is the purpose of these things. Let me write them first. Total underscore accuracy underscore validation and total underscore loss underscore validation. Perfect. Now what are these? Total accuracy training is a number that will be incremented throughout the epochs. It starts with 0, we don't have any accuracy, and after each epoch we will increase the accuracy, and to know after each batch we will increase the accuracy to know and in the end we can know the final accuracy of all the batches inside this epoch, which means all the data. Okay, let's start. For index comma data, or no, let's not use the index is not necessary here. For data in train underscore data loaders, data loader. Okay, you remember data is having input and output. Okay, so we're gonna use inputs comma labels equal data. Okay, we are going to extract data. Data is having 2 values, which is inputs and labels, which are values of 8. Don't forget, inputs is 8 rows, labels is 8 labels. Okay, because the batch size we specified above is 8, and this comes from the train data loader. Great. Now we're gonna need to move inputs. No, we don't need to move inputs to device because we already removed them. Okay. And then we can do the prediction equal model of inputs. Okay, now let's see if everything works still here. It's usually recommended that you stop at some point and try to run the things, because if it's not working, you can have you can easily modify before you continue. So let's see. Okay, this is wrong. Okay, break. Great, it's working fine. And then we are able to do the prediction. Okay, so we have our data. We gave the data to the model. The model outputs a prediction, which is definitely wrong because the model just initialized, it's not yet trained. Then we are going to calculate the batch loss is equal to criterion of prediction, comma, labels. Sorry, I don't know what's happening. Okay, and then we can do, let's try to run till here. Okay, you see the error using target size of torch size 8 that is different to the input size of 8 by 1. So we need to make our input having this one. Okay, the input size is 8 only. We need to have it with that shape, 8 by 1. Okay, PyTorch cannot do this automatically. So what we can do is that when we output the prediction, we does this. We does the following. We does a squeeze function of 1. Now let's try. And it's okay, it seems working, but we need to stop it because we need to do a break to stop the loop. Now, yes, working. Okay, what is the purpose of this squeeze? Now, let me print before and after squeeze, and you can understand better instead of explaining. Let's print prediction and print or let's print prediction shape better, because it will not fill the screen with very confusing things. Prediction shape and print prediction dot squeeze of 1 dot shape. No, runtime. We need to put a break statement. Break. Okay, let's run. Okay, let me comment this because this is having a problem. Okay, do you see the difference? The difference here is that if we take one instance from the beginning or anywhere, if we take one instance, this is the first one. Okay, we need to break after this one, okay, because it will be better for you to understand. Okay, great. Now, do you see the difference? The difference is the default value of prediction is 8 by 1, okay? The value is 8 predictions, 8 labels by 1. But our after squeeze, it became 8 only, okay? Why? Because when we compare prediction with labels, like in the same cases, guys, in the two cases, the values are same. It didn't change, but we just changed how the data looks like, or the shape of the data. We just changed that, but the data is the same. It's not changing, but we changed how the data is represented, because the labels are just 8 rows. It's not, it's just 8 rows. It's not having any problem, but the predictions is 8 by 1. There is an extra dimension, so we need to squeeze it and remove this one to become 8 only. Okay, great. Now we can continue. We can remove that one and uncomment this one back. Okay, now let's remove this break also. Let's go next. Next is, so we calculated the loss. Now we are having the loss. Now we need to total underscore loss underscore train is equal to, is plus equal batch underscore loss dot item. Okay, what did we do here? Do you see total loss train that we had here? This loss is the loss after each epoch. So after each epoch, we make the loss and accuracy 0, and then we calculate by adding the loss of the previous batch, of the loss of the previous batch and accuracy of the previous batch. We keep adding the accuracies of each batch until we finish all the accuracies and the losses, and we have the final loss or the accuracy of the final. final thing. Okay. Okay, so batch underscore loss dot item means that we get only the number of it. Okay. Okay, so you can think about it that we have eight rows are being forwarded to the model. We are having 8 rows. We do on these 8 rows forward propagation, and after we do the forward propagation, we compare these losses using the loss function. Sorry, we compare the output with the original output of these 8 rows, and when we compare them, we have the loss or the error. We add this loss to our loss, because this is the loss of only 8 rows, not for the whole data. We add it to the loss of the total loss train, and then in the next batch, the next 8 rows, we do the same, and we add it to the previous loss, and we keep adding until we finish all the batches. We have a final loss value for this epoch, and then we make these values 0 again, and then we do the same process for the next epoch. Remember, you are looping through 2 things. I don't want you to confuse here. You are looping through 2 things, not through 1 thing. And okay, now we have the total loss train. Then accuracy is equal to, how we can calculate the accuracy? We need to calculate the accuracy between the predictions and the labels. So we use the predictions, but predictions here are decimals or float. So we round them to 0 or 1. We use the round function, and we make sure if it's equal label. Now this line will output to you, sorry, it's prediction only, and it's labels. Okay, this line will output to you an array of 8 elements, which is having either true or false. Let me show you. Accuracy, let's print accuracy, and break, and break. So break allows us to stop the loop after first iteration so that we don't wait for so long. Okay, just we are still testing our stuff. Okay, we didn't do anything. Okay, you remember we removed the squeeze, so we put the squeeze thing here. Perfect. Do you see this? A list of false, true, false, true, false, false, true, true, which means that the rows are the following. There are 8 rows, and the predictions are, the first one is false, true, false, and so on. Okay, great. Then we want to know how many are true, because this is the accuracy. So we use sum. So let's see. Sum will give us what? Sum will give us 3, which means that we have 3 true out of 8. Okay, and then we use dot item, which will give us, at the end, will give us 4. Okay, the number is changing. Don't worry, because every time we start training from the beginning, we start training with the data being changed the order. So it's fine, it's okay. I mean, if it's if you want, we can do it in an easier way here so that I can show you better. So let me print accuracy so that the number will be saved and not changed. Do you see the accuracy here? True, false. So how many we have? 1, 2, 3, 4. If we add dot sum, will give us 4. Dot item will give us the exact item 4, which means this number. Okay, it will convert it from a tensor in this strange format. It will give us the final number in just an integer. Okay, so that's it. We will use this way. Okay, so we're gonna copy this one, cut this one, and paste it here. Now, great, we have the accuracy, we have the loss. Now, don't forget, we need to add the accuracy to the total accuracy of the validation of the training. Because remember, this is the accuracy of the batch, accuracy of 8 items only, not for the whole. So we add it to plus equal to this 0. We keep increasing the accuracy. Okay? Okay, perfect. Now, are we done? We are not done yet. We just did the forward propagation, and we got the accuracy and the loss. Now, the next part is batch underscore loss dot backward. What does it mean? Now we need to do the backward propagation, okay? Don't worry, there is nothing difficult here. We are going to the other side, or we are going from the other side of the model to do the backward propagation. And at this point, the optimizer will come. So we need to do optimizer dot step, which means optimizer, please take a step and change the weights because we already have the loss. Optimizer dot 0 underscore grad. Okay, what does this line means? Means that after the optimizer changes the weight in this batch, the optimizer restarts again. This avoids having writing this is better for not having like the model will converge by that way. If you didn't do that, the model will not progress. Okay. Okay, perfect. Now we are done with the training. The training is working perfectly fine. Okay, let's try to do one batch of training and it's working fine. Great. Now the next part, guys, is the validation. Okay, we have a validation data set. We want to do a validation. Okay, now validation means that we make the model. After getting trained, we make the model does a prediction, and after this prediction, the model will not do a backward propagation. It's just a prediction. You are testing the model during the training. That's it. Okay, you are doing a test of the model, but the model is not yet trained. Okay. Okay. Now with torch dot no underscore grad. What does this mean? This means that with torch dot no grad means that use the PyTorch model, but not for training, just for testing. So it basically it prepares the model for doing a prediction, but without changing the weights. We will just do the prediction. It's like we are using the model for inference. Okay, for inputs, comma labels, or no, let's put it the same way as we did before so that you don't get confused. In validation data loader, we are going to have inputs, comma labels from data, and then we are going to do prediction equal model inputs dot squeeze the same way. Okay, we are doing everything the same. Okay, in fact, you can copy the same code up into here, the same code, that one into down, but without these three lines. Okay, but of course total accuracy will be validation, loss will be validation. Okay, then we calculate the loss. The loss is used here just for seeing the progress of the model, and it will not be used for backward propagation. Okay, just want you to keep in mind that. Labels, and then we are going to have total underscore loss underscore validation is plus equal batch underscore loss dot item, then accuracy of we are going to do accuracy is equal to 2 brackets like we did above, so we can take this copy, no issue. Okay, and everything is same. Then we can write the total underscore accuracy underscore validation is plus equal accuracy, and that's all. Okay, now we are having the validation part. Okay, okay, great. Now let's try to run this and keeping the break function. Okay, break, let's see. Okay, and perfect, looks good. Okay, so everything is working. Of course, we'll remove these breaks at the end, but for now we just want to make sure that the code is working without any errors. Now we can remove them. Okay, no problem. And we can go back and write inside a epoch level, not a batch level, because remember here all of this is batch level, and this one as well is batch level. Okay, so means that you have two loops, you have nested loops, don't forget. So we are going to the main loop now. The main loop is the loop for the epochs, and we will start appending the values for plotting. We're going to append total loss train plot dot append. You remember the lists we created here, okay? Dot append round total underscore loss underscore train divide by 1000 comma 4. The comma should not be here. Yeah. Comma should be inside. Okay, I'll explain this to you, don't worry. Now let me do the same for all of them. Now let's change the lists. Total loss validation will be here, and we will use total loss val, and then we are going to use total accuracy train. We are going to use, okay, now how we are going to use the accuracy? Accuracy will be a number, okay? So the number should be, okay, let me show you. Total underscore accuracy underscore train multiplied by training underscore data dot underscore get underscore item underscore like that. Okay, multiplied by 100 comma 4. Okay, what did I do here? Okay, it's nothing, it's just the percentage formula. So actually I'm using, in the first one, I'm using the round function, okay, to do the following. I'm taking the loss. The loss will be a very large number, okay? It will not be that large number, but it's still, you see here, total loss train, 676.150. Okay, it's better that we divide the loss by 1000 so that it will be normalized. We are taking the same concept of normalization here. And round comma 4, we are using this one to do the rounding part, okay? So we take only 4 numbers after the decimal, not more than that. And then validation, we are doing the same, but with the total loss val. Accuracy, we are doing the percentage formula. So we are having round total accuracy train, with the total accuracy we got from the training, divide by training underscore data dot, sorry, it should not be get item, it should be get len, I believe. Len only, without get len. Len. What is this? It means that we get the length of the data that we have. Okay, so the total amount of the data we have. So if, let's say, if we have 10 rows, we got 6 correct. So 6 divided by 10. Okay, and then multiplied by 100, which will give us at the end 60%. If we take the example. Okay, so we are calculating the percentage, and we are doing round 4 as well to take only the first 4 values. Now we can do the same with the validation train here, and you can see here that the total accuracy will be for validation, and this one is going to be validation underscore data dot len. Okay, do you see now the good thing about using the data loaders, about using the dataset objects, about using the things that PyTorch provide? You feel that the things are totally customizable, and at the same time, everything seems useful and working good together. It's, as I told you, it's like an ecosystem, okay? Okay, great. Now we can print the stuff, okay? So let's print the things. Print epoch number, okay? And this will be, let's put it like that, epoch plus 1, because it starts from 0 and we want to print it in a very nice and neat way. Train loss is, we are going to take that part for the train loss, okay? No, not the total loss train. Yes, we are going to take that part here. And then we are having the train accuracy, which we will take this one also, training accuracy. Do you see that one? You see what I'm doing? Okay, I'm creating the loop. I'm creating the print statement for the training, okay? And maybe we can put a line, okay? So let's put 3 quotes and 3 quotes, and we can put a line for easier writing, and then we can write validation loss is equal to, we are going to take this one, and validation accuracy is going to be this thing, between curly brackets, okay? You can print it in any way you want, okay? This is not something, this is not a problem. You can even skip the printing part, okay? This is just for giving some good look, and you can see the progress. So let me print also after each epoch, can print maybe 25 equal signs, okay? And let's try to print the training loop. Okay, yeah, perfect. Now you can see here that the training is started, okay? The training is very good actually, okay? And it's not changing that much, you know, because it's the data set, the model needs modifications, the learning rate maybe needs to change. So don't expect the model that it will be very good, because we should have like a whole session for optimizing the model and making it better. Okay, now maybe I can change the batch size. Maybe you can make the batch size 32, and we can try again. So 32, 32, 32. Let's run everything again, and let's see the model progress. So it starts from the beginning, and it increased up till 98.71. Okay, so okay, it's good. The model is good. As I told you, you can play with the model, you can optimize the model. The goal is for the PyTorch syntax. Okay, and that's all. Now we can proceed with the testing. Now we can see that the difficult part has passed. Start with the testing. Okay, so in the testing, we will use the testing dataset to test our model. Okay, so let's see. Now we will start with torch.no_grad. As well, this is the same part as what we did for validation inside the training loop. And then we will write total_loss_test is equal to 0, and total accuracy test is equal to 0. Okay, and then we will do the for loop for inputs or for data in testing_data loaders. We will be having inputs, labels is equal to data, and then we will have predictions. Prediction is equal to model of inputs. Same way we are doing everything is same. Inputs dot squeeze of 1. Then we will write batch_loss_test is equal to criterion, the same loss function we were using, of prediction, labels dot item. We are going to take the item of that one. And then we are going to have it, because don't forget that this one is also batches. Okay, we are doing this as batches. Now you can have it as batch 1, doesn't matter, but we are having it the same concept as we are doing for validation. So we will add it to total loss test. So total loss test is plus equal batch underscore loss underscore test. Great. And then we are having accuracy the same, so maybe we can get the accuracy also here and that one here, and we can change accuracy prediction same, but this one will be here. Okay, and that's it. So I believe nothing is missing, so we can print accuracy. The testing accuracy is round. Also we can do the same round of, okay, we can get it from up here. Now we have to be efficient. You can get it from here, so you don't waste more time. Okay, and write it here, but this one instead it will be accuracy test, and this one will be testing underscore no, not testing underscore data dot len by 100. So you can see here that testing data loaders is not defined. Okay, testing data loader it's supposed to be, I think. And it, yeah, perfect. Now the accuracy is 98.79%, which is amazing, of course. And this is, you can think about it, this is a small data set, small model, not a very complex problem, so it's not difficult to get a very good number of accuracy. But still you can play more with the hyperparameters, with the network, with the things, and you can get better results. Okay, now comes the visualization part. Okay, so first let's create figure, comma AX axis is going to be plt.subplots. We'll explain this, no problem. Number of rows equal 1. Sorry, equal 1. Number of columns equal 2. And figure size, fig size is equal to 15 by 5. Now, what I'm doing here, I'm creating a plot. Okay, two plots. I'm creating a figure. The figure is having one row. So one row and two columns. Each column belongs to one plot, and this is the figure size. Okay, it gives me the figure and the axis. Now I will write the first axis of axis 0. I will plot here what I will plot the axis 0. So it brings the screen like a grid. Okay, like one row and two columns, and the first row, the first column, I'm dealing with it with this one, axis 1, axis 0 dot plot. What I'm going to plot here, I'm going to plot total underscore loss underscore train underscore plot. This was the list we got from above, you remember? Label equal training loss, and then I am going to have axis of 0. I'm going to put some labels and put these things later. So, but for now, let's put this. This is the training loss, and I'm gonna need the validation loss, total loss val. Then we can put the labels. So dot set title. Now these things you don't need to memorize, okay? Because you can get easily these things from Google, not a problem. I think it's called validation. You can get it copy paste from Google, but you have to understand these concepts, okay? And then you can search for the things in Google. It's fine. Training and validation loss, maybe let's say over epochs, maybe, okay? And then we can write axis of 0 dot set X label. What do we want on X label? The X label is going to be the epochs, okay? And we are having as well the Y label. Same, almost same. Just change this to Y. And we are having loss as the Y label. And then I think it's pretty clear when you write it, okay? I advise you that you rewrite the exercise again, even if it's on GitHub, but you rewrite it again. It's better so that you practice you practice the structure, this structure, okay? And you can set a limit as well. Axis of 0 dot set underscore y limit. Okay, why do we need y limit? Because we want to specify where y should stop. So let's put y between 0 and 2 maybe. Okay, and axis of 0 dot legend. Okay. Okay, now that's it for the accuracy. Sorry, for the loss. We're gonna take the same and we are going to put here 1, axis of 1. In all of these, instead of rewriting everything again. Now here we will plot the accuracy. So total accuracy and total accuracy. We're gonna rename it here to accuracy. I'm gonna take this into here and epochs accuracy, and the limit will be 1 to 100 because accuracy is in percentage, and we're gonna write here accuracy. And that's it. We can do plt.show. Now let's see the results. And expected n calls. Okay, I believe it's without an underscore, I think. Let's see. Yeah, perfect. Now we have the training loss and training validation. So you can see here that the validation, the training loss, training validation. So you can see here that there is no overfitting, and the model is going good, quite good in training loss. But the validation, the red line is not shown. I'm not sure why, but let's see. Let me see the accuracy. Accuracy is almost same. So I think it's showing, but maybe it's not very clear. So probably we need to set the spacing between the diagram or something. I'm not sure, but let me try to put 50. I'm not sure. I'm trying this together with you, but okay. Anyway, it's not the problem. It's not that problem now because it's not showing here total accuracy validation plot. Okay, let me see. Am I total accuracy validation plot? Yeah, I didn't append it. Do you see here the problem? It's an empty list. I didn't append it. That's my fault. Sorry guys, that's my fault. So let me see here. It's not total accuracy validation plot. Should be that one. And we can run the training again. And then we will have some results here. Now the training already, now it's running for the second time, so there is no increase. Maybe you can run again from here and you can see difference. But okay, let me run again to see the different plot. So we can run here loss and optimizer and these things. The training loop, yes, it's starting from the beginning now. And we are checking the accuracy again. And run that one. Okay, let's make it from 0 to 100. Okay, let's see. Yeah, now it makes sense. Now there is no overfitting and the other line appeared. So do you realize the problem? The problem is that I didn't fill this list. I didn't append any value to this list, as I appended accuracy training and accuracy validation inside the same list, which came as wrong, obviously. So that's my fault. That's a typo, but luckily it was not a big deal, not a big problem. And that's it. Now we are having already the training. Now, what if we want to do an inference? So we want to use our model in production, okay? Or we want to use it on a mobile app, or we want to use it in whatever. I want to do one single prediction. I don't know the result. I want the model to know the prediction for me. So let's say we have area of whatever, 6, maybe this number. Okay, I'm writing just random numbers. And we have measure axis length. Okay, now comes the thing, okay? Before we write these things, you remember the original df? You remember that? This we will be using to do the normalization, because we did the normalization using the same values from here. So we will use it to do the normalization again during the inference. So how are we going to do that? Let me show you. Now we will write area equal a specific number, any number maybe, I don't know, that one maybe, and we'll write original data frame of area divide by original data frame area dot max or dot absolute. We did the same, dot max. And we are going to do the same here with measure access length. Let's write any number, maybe 81, and we put this one here. And then we are going to do the same here, measure minor access length. 42, let's say, anything, doesn't matter. Okay, and do you see what I'm doing? Now, these numbers, as a user, you should insert these numbers, and at the end, you will find the prediction. So you can put, let's put more things. Let me take it from the data frame, so it would be better, just copy pasting. Okay, minor access length, and this thing, can write here 32, and convex area, we can write here, let's say 12. Sorry, need to copy this, paste it here, and so on. You can continue with this process. Let me write it quickly. Yeah, this is missing this thing. Okay. Let me put. Okay, and then we will have more columns. So let's write these. Okay, let's take after convex area, we have this diameter. Put maybe 33. And then we have extent. We put, let's say, 98. And then we have perimeter. We put 927. Roundness, and we put this as maybe 677. Now, any numbers, that doesn't necessarily. I just want to show you the final result on how to do a prediction, okay, without using the dataset, okay? And maybe we can keep 24, okay? And that's it. Now we're gonna use model.predict, or we can only use model, no need to use predict. Predict is used in TensorFlow. Can use model only, and we can take these values inside the list here. Area, measure access length, minor access length, this thing, convex diameter. I know this may takes a little bit of a while. You can skip this section, by the way, no problem. But this is just for you on how to do the final inference, okay? Roundness, because it's important to know how to integrate this inside a mobile app or a normal software. Okay, now that's the list. Don't forget, what did we do inside the data preprocessing part? We did the following, okay? Now, we can do the same, actually. We can take the dataset object and create it, or we can create without the dataset object. Since you already know how to create the dataset object, we will do it without the dataset object. Okay, now we convert it to tensor, and then we moved it to device. Because the model is on the device. Don't forget, the model is on the GPU, is not here. It's on the GPU. So to use these values, you need to move them to the GPU. So let's do the same. We are going to have a list. We're going to do torch.tensor. We are going to have dtype equal torch.float 32. And then all of this tensor, we are going to move it to device. Same way we did in the dataset. Okay, and that's it. Prediction equal, or let's call it my prediction equal, and then run. And here we go, working fine. My underscore prediction what is my prediction? My prediction is 0, which means from here, it's not Jasmine, it's Gonin or this thing, okay? And we can do dot item to get the tensor that is only 0. And that's it. So sometimes this number can come as a decimal, okay, which may be 0.70 something, okay? You can use the round function always, so you can do like that. Round, and here you go. You have 0, okay? So this is important that you use it. If your output is something like the 0.73, is the same way we used above. It rounds it to 1, okay? Okay, that's it for this lecture. So you are going to find the repo for this complete exercise explained in very deep details on in the description. You're going to find as well the other videos, the video related to how to use the datasets inside Colab directly, and also the video on how to install Python and IPython or the Jupyter notebooks in case you need to work locally. I always advise that you work on Google Colab, but if you want to work locally, make sure you install CUDA properly, okay? That's it, and thank you for watching. Subscribe and like for more videos like this. Thank you. If you have any ideas, specific ideas in mind that you want me to implement, please write in the comments. Thank you. And welcome back to this series. So in this lab, we will be creating or we'll be building a multi-class classifier, an image multi-classification problem with PyTorch. So how we're going to build that? So first of all, this is our data set. So the data set is called Animal Faces. It's available on Kaggle. So you can go on Kaggle, the link, you'll find the link on the description. And then you can find it here with all the details. So the data set is divided into cat, dog, and wild. Okay, so you have some samples here in the in this page here, and also you have a lot of details also inside this link. You can check it out. I already downloaded the data set from Kaggle the same way we have done last class, and the data set you can find it here, animal classes, and here it is. Okay, now let's start by doing the imports. Okay, so first of all, we are going to import torch. Then from torch, import nn. From torch.optim, import Adam. Now I'm going to explain why we are importing each of these, but let's finish them first. So from torch vision, import dot transforms, import transforms, and then we are going to write from torch dot utils dot data, import dataset and data loader. We will need the sklearn dot preprocessing, import label encoder, import matplotlib.pyplot as plt, and then from pil import image. We're gonna need also the basic things, pandas as pd and numpy as mp, and finally we'll need the os. Okay, now why this is, first of all, this is the main PyTorch library, and then we are importing NN, which is having the layers and the loss function, and then we are importing Adam optimizer, be used in the training, and transforms we are going to use it in pre-processing the images. Dataset and data loader to create custom datasets, and the data loader is the object to loop through the batches that divide our dataset to batches. Then from sklearn pre-processing label encoder, we are going to use this in converting our data, our outputs from strings to integers, integer encoded. And so instead of having cat, dog, wild, we're gonna have 0, 1, 2. And then we are having this one for matplotlib for plotting. Then this one is to read the images. These two are for data preprocessing, and finally the OS to read from the directory. You're gonna know why we need each one later this lab, okay? Now, let's, as we mentioned before, PyTorch doesn't automatically detect the GPU. So you have to tell it to use the GPU. So you have to first declare which device you are going to use. So you're gonna write CUDA, that this device is CUDA, if torch.cuda.is available, else use the CPU. Okay? Now let's print device available is device. Now let's see, sorry, this is a typo, should be device, yeah. Now let's see what is the available device. So we have a typo here, import from, okay, this is supposed to be from, okay. And no module named transforms. So I think there is a typo here. Yeah, transforms. Okay, so we are good. And yeah, we have another problem here. So from pel import, yeah, this is supposed to be image. Okay, these are typo things, so not a big deal. And yeah, perfect. So we have CUDA here, the CUDA device, which is the T4 GPU. Okay, great. Now, what we need to do? First of all, we need to read all the data here. Okay, so this one contains cat, dog, wild, and this one contains cat, dog, wild, and each one containing its own images. So we're gonna need to split the data set on our own. So the data is split into train and validation. We need train and validation, or train and test. Now we're gonna need to split it to train, validation, test. We need this 3 splitting, okay? So we can do this by reading all the data, everything we have with its corresponding label, and then we split on our own. So we can read all of this inside a pandas data frame. So let's see how we're gonna do this. So image path is equal empty data frame, and labels is equal empty data frame as well. Now for I in os.list there, for what? First, we're gonna go into the first layer of the folder. Now, this is a matter of layers. You have to think about it as layers. So you first go inside this one, you loop inside AFHQ, and then inside this loop, what you're gonna find? You're gonna find train and validation, which is in this case, I. So we are going inside each one, inside the train, what do we have? We have the labels. So we're gonna loop through the label. So for label in os.list directory of f of the same path, but adding to this path I. And then we are going to do the same for image, because each one of these is containing images. So for image in os.list directory or list there, and we are going to have f and the same part, but we will join it with I, comma what, comma label, okay? Now, what will this print for us? Because I think you may be confused of the syntax. So let me print image, and then I'll do a break here, and then a break here, and then a break here, so that you can, I just want to show you, I just want to show you the outputs after each layer. So we can have here print I, and then print label, and then print image, okay? So let's see. If we did this, yeah, this is supposed to be like that, yes. So do you see that? So we have the first layer, which is AFHQ, and inside AFHQ, it gave us val, which is the validation. And if you continued, so if we didn't break this one, it will give us val and then test, and then train. So let's see. But then this is gonna take some time. No, okay, great. Now it gave us validation, then wild, then this one, then train. So it's looping through that one, okay? I think it's better if we kept the break. You will not get confused. So inside validation, we are going through what we have here. So we are going through the same folder I. So inside validation, what is here? wild dog cat. So it took wild. So I think it's sorting it in some way. But anyway, it took wild because it got into this folder. And then we have image, which is this one. So inside wild, it got that image. So I hope this idea is clear, okay? We want to read each image, okay? Now this is the label, okay? So I want you to remember that this is the label, okay? Okay, great. Let's remove all of this stuff. And we can remove this as well. Okay, now what do we want? We want to append the image path that we got. So for each image, we want to append this image, okay? This complete path of the image, okay? And then we are going to append the label corresponding to it, which is this one, okay? Now, this method may seem complex, okay? If you find any other method, or if you want to use any other method, it's totally up to you. This is on how we read the data, but this is fine, okay? I want to split the data, so I think, in my opinion, that this is a good way. Maybe there is better, but it's fine, okay? This part is not necessarily has to be done like that. It's up to you if you find your own way, okay? Now, after we have read the image path and the list and the labels, so we are going to have a data frame which contains everything is equal to pd.data frame of what? Of zip image underscore path, comma, labels, and we are going to have the columns is equal to image underscore path, comma, labels. Okay, and then let's see our data frame dot head. Perfect. So now we have the path of the image and its corresponding label. So before also we proceed, let's see the values, the possible values of the labels. So print data underscore df of labels dot unique. It's supposed to be 3. Yes, perfect. Wild dog cat. So we are good to go. Okay. Now let's continue. So what else do we need to do is to split our data. So the purpose of doing this is to split the data. So we need now to split our data set into 3 data frames. A training data frame, a validation data frame, and a test data frame. So let's train equal data underscore df dot sample. Now here, for simplicity, we will not be using the train test split. We will be using that one, okay, the sampling function. So because train test split will give us 4 values. So the x train, y train, x test, y test, and we want the whole data frame. So instead of having train test data, train test split that we did in the last lab, we will do this so that it gives us directly the data frames instead of giving us lists, and then we convert again to data frames. So this is faster. Now train is df.sample of fraction 0.7. What does this mean? So for the training data frame, we want a sample from the main data frame that we have. So this data frame, we want a sample of it, and this sample is 0.7 of the whole data, which means 70% of the whole data. Okay, and then we are going to have the test equal data underscore df dot sample. Sorry, not dot sample, equal data drop what? Drop the train dot index. Okay, now what did we do here? So we took a 70% amount of our data, of our original data frame, and we called it training. And then these training values are having indices, right? Like these are having indices. So we are going to drop these indices and put them inside a variable called test. Now we split the data because the pending part will be 30%, so which will be the test part. Now we're going to do the next part. It will be the same, but for validation. So validation, we are going to take a sample from the test now, okay? So test.sample of fraction equals 0.5, because we want to split 70%, 15, 15. So 50% of the 30 percent that we took is 15%. Okay, now test equal the same, equal data underscore df, test dot drop val dot index. Okay, and that's all. Now we can print the shapes so that you can understand now how the data looks like. Dot shape, print val dot shape, and print test dot shape. Okay, perfect. Now we have 70%, 15, 15. Okay, so we are good to go now. We have the data frames splitted. Now what is next? What do we want next? So first of all, let's declare our label encoder. Okay, and then we will have the transform function. Dot compose. Now I'll explain to you what is this, but before we write here, we need to fit the label encoder into our data. So label encoder dot fit on what? On the data underscore df of labels. Now, what does this mean? It means that we want our label encoder to give the values for the labels that we have in the data in the data set. So the labels we have is wild, cat, dog. So we want to fit it there so that the label encoder changes automatically. Label encoder will store that automatically. Cat translates to 0, dog translates to 1, and wild translates to 2. Now this could be in any order, not necessarily that order, but with this concept. Okay. Now we are going to use the transform. Now what does transform means? What does it do? Okay, so it makes all the images having the same properties, okay, which is the size or the data type or whatever. So we'll start by doing the transforms dot resize. Okay, we want to make all the images are having the same size. Okay, now let's put this inside and brackets. Yeah, and then we are going to have transforms dot to tensor. Okay, sorry, and then we are going to have transforms dot convert image data type into torch dot float. What did we do here? So for each image we read, we will change the size into 128 by 128. We will convert it into tensor instead of normal matrix or numpy matrix. And then we will have it as a float, a torch float type. Okay? Okay, great. Now we didn't read the images yet. We are just declaring the objects that we will be using. Okay? Now let's create the custom dataset. We have a custom dataset, right? So class custom image dataset, which will have dataset, and we are doing the same part we did in the last lab. So we are creating a custom image dataset because we want PyTorch. We mentioned before that PyTorch is like a big ecosystem. So all the objects understand each other perfectly fine. So it's better that we have our data converted into PyTorch syntax or PyTorch dataset. So first we will have this dataset, we call it custom image dataset. It inherits from dataset. So it takes the same functions that we have in the original dataset from PyTorch, and we will just modify these functions. So def init, which is the constructor, we will have it self. It takes self data frame and transform equal none. Okay, by default the transform equal none. So we assume that there is no transform, but there is no transform object, but we will give it a transform, so it's fine. But this is just for having an efficient use. Now self dot data frame equal data frame, and then self dot transform equal transform. Now we are defining the objects inside this class. Self.labels. Yeah, now what will be the labels? Will be torch.tensor. Now torch.tensor of what? This is supposed to be small. Torch of tensor of what? Of label underscore encoder dot transform what? Dot transform data frame of labels, and then we are going to transfer it to device. Now what did we do here? We are creating a torch.tensor. The torch tensor is from what? From the data frame of labels, which is this one. So, but we will use the label encoder to transform them. Transform means that we are going to make them into integers instead of strings. So instead of wild, it will be 0. Instead of cat, it will be 1, and so on. Okay. Now, next is def underscore underscore len. Now, this is a built-in function as well. So we have to use the same syntax. So what does it return? It returns how many rows we have in the data frame, which is self.dataframe.shape of 0. Now, the last function is def of get item. This is fully customizable, guys. So that's why PyTorch is very nice, because you can customize everything. You can put your own conditions on how we create this custom data set. You can put like whatever you want and whatever things you want inside in PyTorch easily. So self, it takes self and index, the index of which item you want to get. This is same as well. It's already written inside the dataset class, but we will overwrite it to match our needs. Image path equals self.dataframe.ilog. So which image path? Where is the image path that the user, the index? In which path in the data frame? So we're gonna get it according to ilog function for that specific row, all columns. First column, which is the image path, because the first column is image path. And then we're gonna have label equals self.labels of idx. And then we are going to have image equal image.open img underscore path dot convert RGB. Okay, then we will have if self dot transform, which means that the user provided a transform, it's not none. Then we are going to apply this transform on the image and move it to device, because I want to move everything into the CUDA device. And then finally we are going to return image comma label. Okay, perfect. Now we are good. So what did we do here? We took the image path according to that specific given index, and we took the label according to that specific index as well. And then we are going to have the image, open the image and load it inside PyTorch. And if we have a transform object, which in our case we have, we are going to do self-transform. We will have the transform properties of this, we will make the image into this transform properties, and then we're going to move it to device and return image label. So perfect, that's all. Now, working fine. Now, let's create the data set for training. Custom image data set, and this one will take data frame equal train, and we're going to give it the transform equal transform, because we already have a transform. And then we are going to do the same but for validation. So we are going to have val here, and then for test, and we are going to have the test here. And that's all. So let's wait for it. Okay, it didn't take long, so great. Now we have our data set ready. So let me show you one thing. So if we want to use, because PyTorch inside the training will use this syntax by default, but now let me, like, if you want to use it, So data frame dot underscore underscore len, for example, and like that. What we'll have? So the training is this one. And what if we want to use get item? And we are going to use item number 2, for example. So this is the image, and this is the label, which is 0. And we don't know what is 0 till now, but I'm going to show you if you want to know the 0 corresponds to which label. So label encoder dot inverse transform for 0. And let's see what will be the output. It's gonna be cat. So this image corresponds to a cat. So now I hope the idea is clear of the custom data set, and then we can move on. Now, what is next? Next, let's visualize the images. Now, this step is optional. You don't have to visualize the images, but this is just to have a look on some random images from your data set. Okay, so let's write n, and this is where we're going to use the matplotlib library. So we're going to have n rows, number of rows. We are going to display it in a grid form of a matrix of 3 by 3, and n columns equal 3. And then we are going to have the create the plot by itself. F comma axarr is equal to plt.subplots, and the subplots are of the size of number of rows comma number of columns. Then we are going into a loop for each row. So for row in range n underscore rows, we are going to have for col in range n underscore cols. So we are looping through each row, then each column. And then we want to read the image. So image equal image dot open. We're gonna need a random image. So data underscore df, random image doesn't matter from training or testing or anything. So random image dot sample, since we want a random image of amount equal 1, n equal 1. We are not using here fraction, we are using n, which is amount. And then of image underscore path, so we're getting a total random value from the image path dot iloc of 0, which means that iloc indicates that we are going to use this item, the index of that item, dot, and convert it to RGB. Okay, great. Now we are going to put our image. So axrr of row of that row and that column is dot imshow image, and we don't want the axis. We don't want to show us this like x axis and y axis. We don't want this. So you're gonna need to close them. So we're gonna have the same of this one dot axis off. You're gonna turn it off, and then we are going to have plt.show. Every time you run this, it will display random images, different random images. So let's see. Yeah, there is a path. I think we have copied it wrong or something. Yeah, image path, not path. Okay, so perfect. Now we have the images. If you run it again, different images. If you run it again, different images, and so on. Okay, so great. The images looks good. They are of a good quality, so we can proceed. Okay, so now let's set our hyperparameters. So we're going to start by setting the learning rate as 1e power minus 4, and we're going to have the batch size as 16, and also we can set the epochs for 10. You can change these, of course, and that's it. So nothing more we can do here. Then we're gonna have to build the training data loaders, or the data loaders for everything. So data loaders, we discussed this previously. Data loader is used to loop through our data easily. So we're gonna start by the training loop through the data by batches, not just looping. Data loader, we imported this object before. It's gonna take, because data loader takes a PyTorch dataset. So that's why we converted our dataset into a dataset first, into a PyTorch dataset. Now it's taking also batch size equal batch size we created, and then shuffle equal true. So we are going to shuffle the data, change the order of the data because to avoid biasing, and then then we're gonna do the same for val and test. We're gonna have val and we're gonna have val here, and then we are going to have test, and we are going to have test here as well. And that's it. So we are good, and we have our own data loaders. So what's next? Now, next step is going to be building the model. We're going to start to write the model class, okay? So like we did in the last lab, let's first start by writing the class, and let's call it network or net, and it inherits from nn.module, okay? So it inherits from the nn class of the nn.module class. The main class is nn module, and we are going to overwrite the functions inside it. We're doing the same that we did in the custom class dataset, okay? Great. So first, of course, let's start with the constructor. Def initialize or init self, and then it gonna take super dot underscore underscore initialize. Okay, so we are going to use the same constructor that we had for the original class, but we are going to add some things to it. So self.conv1 is equal nn.conv2d. We are going to start adding the layers now. So here, remember, we are just here declaring the layers. We are not doing how the data will flow inside the model. The flow of the data will do it inside the forward function, but now we are in the initialize function or the constructor. Okay, great. So the first convolution layer is going to take 3 channels because it's an RGB images, so 3 channels are GB, and it outputs 32 channels. This number is optional, of course, and the kernel size is 3, and that's all, okay? Great. Now self.conv2, the second convolution layer, is going to take 32 input channels coming from the first one and output 64, and the kernel size is 3 as well. Self.conv3 is equal to nn.conv2d. It's going to take 64 and outputs 128, and the kernel size is going to be 3 as well. Okay? Okay, perfect. Now, before I continue, let me tell you about the basic convolution neural network structure so you get an idea about that, okay? This is a recap. I assume you already know that, but this is just a quick recap. Okay, now this is from miro.medium/v2, these things, okay? I'll attach these links in the description if you're interested to read more about them. So the convolution starts by having an image, and we do a convolution operation inside the convolution layer and extract multiple channels. So you see this image is 28 by 28 pixels, but 1 channel because this is grayscale. In our case, it's 3 channels because it's RGB. And so in this case, this number is 1 in this case, and outputs 32, so outputs this number of feature maps. The main purpose of the convolution part is to do edge detection, okay? So if you visualize what is the output of the convolution in terms of images, it outputs an edge detection process. And the more the output channels coming, we call them feature maps or image features or output channels or whatever you want to call it, but the more we have of these, the better, okay? And then we go to max pooling layer, max pooling or average pooling, but in general we go into a pooling layer. The purpose of the pooling layer is that it keeps the number same, okay, but it's reduces the amount of the image, okay? Reduces the size of the image. So it keeps the amount of the features same amount, but reduces the size of them. So we call this dimension reduction, okay? So because it it's better for processing and more efficient for processing. And then we go into the next convolution layer to extract more and more features. So we extract more features, and then we go into the pooling layer. Now remember, the pooling layer originally does not reduce the size. However, when you add padding, it reduces the size a little bit. So the purpose of the pooling is to increase feature maps with the same size. The purpose of the convolution purpose is to increase the feature maps, but with the same size. And the pooling layer is to have the same, keep the same amount, but reduce their sizes. Okay, and then we do the same process, and then we reach into the flatten layer. What is the flatten layer? The flatten, instead of having matrices, it puts them inside a big vector. And then this big vector goes inside a fully connected multi-layer perceptron, and then a normal, dense, or linear layer, and then the output layer. So we have created already 3 convolution. Now let's create the pooling layer. Self dot pooling equal nn dot max pooling, max pool 2D, and it's a square 2 by 2. Now I'm going to show you how the pooling and the convolution works in an image shortly. Okay, great. Now what else? Now we only need one pooling layer, because pooling doesn't pooling is working the same through all the images. It doesn't matter the size of the image. It works the same way for all the feature maps. And then we're going to have a self.relu, a relu activation function. This is optional, but it's recommended. Okay, relu. And then we are going to have the flatten layer. Okay, nn.flatten. And then we are going to have self.linear equal nn.linear. Linear here corresponds to that layer, and then the output layer, which is another linear layer. Yeah, now about this is going to be 128 by 16 by 16. Now don't get shocked of this number. Okay, I will explain how we got this number shortly. Okay, I will explain it better in the forward function. Okay, so no problem about that. Self.output equal nn.linear, another linear layer that is taking 128 from here and outputs len of data underscore df of labels dot unique. It's just getting how many unique labels we have, which will be the number of cat, dog, wild. This will be 3. So if you change the images data set, it can work immediately. It's dynamically changing, so no need to change again. Now let's go to the forward function. Forward self comma x, and then it's gonna take what? Okay, now how the data, the forward function defines how the data is flowing inside the model. Okay, so we need to, we declared that we have a convolution, a pooling, another convolution, another pooling, but we need to define this path from here till the end. So how we can do that? So first let's start by x equals self.conv1 of x. So first the image goes into the first convolution layer, then x equals self.pooling x, then x equals self.relu x. Okay, now it passed through the first convolution, pooling, and a relu function. So pay attention to this. What is the output here? Before we continue, what is expected to be an output here? So we started by the image size, which is 128 by 128 by 3 channels, 128 pixels by 128 pixels by 3 channels. Okay, perfect. Now, what is the next part? The next part is expected to be 32 by 128 by 128. Okay, so convolution increases the number of features but does not change the size. Keep this in mind. So the output channels is 32, but the image size is still the same. Okay, now let's move on to the pooling. What is the output of the pooling? pooling layer does not change the amount of the features, but reduces the size of the feature. So we have here 2 by 2. Then 2 by 2. Then it's gonna reduce this into divide by 2 and this divide by 2. So it's gonna be 64, 64. Okay? Now, up till this point, it's 64 by 64. ReLU function does not change anything. Okay? It changes the values inside the matrix, but it doesn't change the sizes or the amount. Now, next part is the next convolution, which is conv2 of x equals self dot pooling again, and then x equals self dot ReLU of x. Now, what is the size here? Now, so far we have reached to that size. Now, this size is going to change. The convolution increases the number, but doesn't change the size. So this number is 32, so it's going to be what? 64, you see here. The output going to be 64. And this one does not change. These two does not change. They will change after the pooling. So after the pooling, what is the output? 64 going to be the same, but this one is divide by 2 again. So it's going to be 32, 32. And then we're going to do the same process again. Let's copy paste it for simplicity and change this into conv3. And now this one will be increased because it will increase the number of channels. So it's going to increase to 128, and these two are going to be the same, 32 by 32. Now, after the pooling, here we have 128, same amount, but this one divide by 2, so it's going to reach 16 and going to reach 16. And that's it. This number is used here because this is the amount of values inside these matrices that we reach before after the flatten layer. It will make the value like this. It will make, this are the size of the one vector after we make it, after we change from a matrix to a vector. This is the size of that vector, 128 by 16 by 16. And the output is 128. Feel free to change that, no problem. So now x equals self dot flatten of x. We are getting the flatten of x, which will be this output 128 by 16 by 16, and then x equal the first linear layer x, and then x equal self dot output of x, because the output takes 128 and brings us 3 different outputs or probabilities corresponding to each class. And that's all. Return x. Perfect. Now, this is like not it's not difficult. I hope it's clear for you. Okay, we have a syntax error. Yeah, I forgot a comma here. Okay, and that's all. Now let's create our network. So model equal net and move it to device, because we need, don't forget, in PyTorch you need to move everything to the CUDA device or to the GPU device so that we can have the everything on CUDA. Okay, yeah, this is a typo. Super is supposed to be like that. And perfect. Now we are good. Okay? Okay. Now let's see a model summary, okay, to make sure that we have our calculations correct. So let's use from torch summary, import summary, and this is corresponding to the model.summary in TensorFlow. But here you must give it the input size. Okay, so input underscore size is equal to 3 by 128 by 128. This is our input size. And let's see the output here. Let's wait for it to load. No. Okay, we have a problem with the shape. Okay, so we must add padding. Okay, why? The purpose of padding is to put another frame inside the image so that we don't lose any features throughout the convolution part, okay? So it's better that we put a padding of 1 in all the convolution parts. Okay. And run this parts again. Yeah, perfect. Now let's see if our shape calculations are correct. We assumed that the output of the first convolution is 32 by 128 by 128, which is this. Now ignore -1. -1 part is going to be replaced by the batch size or the amount of pictures. So ignore this. 32 by 128 by 128. Max pooling doesn't change the amount, but reduces the size by 2. So 64, 64. ReLU doesn't change anything, so it keeps as it is. And then convolution part, 64, because it increases the amount of features and keeps the size the same. Another pooling, which keeps the amount of the features the same, but reduces the size, and so on, what we explained before. So the output, the input is 32 by 32,768. This is after the flattened layer. And then this is the size of the model, is around 10.75 megabyte. It's not a very small model, but it's fine. 4 million parameters, and great. We are good to go and start the training. But before we start the training, we must define the loss and the optimizer. So criterion equal nn dot cross entropy loss optimizer equal Adam model dot parameters comma LR equal LR. So what are we doing here? We are defining a cross entropy loss. We need the cross entropy because it's a multi-class. If it was a binary, we're going to use the BCE or binary cross entropy. And then we are going to use Adam optimizer, but we are telling Adam optimizer that we want to optimize the parameters of this neural network. Parameters here are also known as weights. So if you want to mention weights, whatever, but it's called here parameters. And we are giving it the learning rate, and that's it. And perfect. So we are good to start the training loop now. So this is the interesting part. So let's start by defining total loss train plot equal empty list, and then total loss validation plot equal another empty list. And I'm going to explain why you are having this, no problem. Train plot equal empty list and total underscore accuracy underscore validation underscore plot equal empty list. Great. Now what's next? Why did we do this first? These lists are to store the epochs, the loss after each epoch of the training and the validation and the accuracy after each epoch of the training and validation, because we want to visualize them at the end and know if there was any overfitting inside the model. Okay, so let's start the training loop for epoch in range epochs. Okay, so we are going to loop by the amount of epochs, and then we are going to define total accuracy train equals 0, total loss train equals 0, total loss validation equals 0, total accuracy validation equals 0. Now okay, first, before we go, okay, why did I do this? Because maybe you are confused now. What is the difference between this and that? So no problem. The thing is that we are doing this for plotting at the end. So we are having a list that appends each value. So we are appending these values inside those lists after each epoch. And those values, we will be printing them after each epoch. But these lists, we are plotting them at the end to see if there is any overfitting or not. So for inputs, comma, labels in train loader. Okay, so the train loader makes us loop through 8 inputs or whatever. Now, what is the batch size we set? We said the batch size is 16. So it makes us loop through 16 inputs and their labels, 16, 16, 16, and so on until we finish all of them. Okay? Okay. Now, we are going to use optimizer dot 0 grad. So we are going to reset our optimizer first, resetting the optimizer, and then we are going to give the model the inputs. So first we are resetting the optimizer. Okay, now this option, you can put it at the end or in the beginning, no problem, in the end of the loop or in the beginning. Now we are giving the model the inputs. So the model will give us outputs. These outputs definitely are going to be wrong because the model is not yet trained. So if the outputs are wrong, we need to calculate the loss, which is the error. So we are comparing the model outputs with the original labels. And then we are going to add this error, total loss train plus equal train underscore loss dot item. We are adding this loss into here because this is the loss of the total loss of the whole epoch. So we need to keep adding of each batch until we finish the epochs. Okay, this typo here, outputs. Okay, great. Now after we calculated the loss, we added the loss.item, so the number of the value inside this training loss. And then we are going to have train underscore loss.backward. We need to do a backward propagation now, dot backward. And then we are going to have the train underscore accuracy is equal to. Now, what is the accuracy? So we need to know what is the accuracy of this batch. Okay. The accuracy is going to be torch.argmax. We need to round it. We need to know which probability of the three probabilities we have. Remember, we have three outputs. Each output corresponds to one probability, like either cat or dog or wild. So we need to get the maximum one. So outputs x is equal 1 is equal to labels. So we need to make them equal to the labels, and this will bring us a list of 16 values. These values are either true or false, and the true ones means that this prediction is true. No problem, I'll print it for you so that you can see these things. .sum.item. So .sum brings for us the how many values are true, and .item brings us the value by itself, a numerical value of how many values are true. Okay, so before we proceed, let me put a break here and another break here and print these values for you so that you can have a clear idea of what we are doing here. So first let's print this, and then we are going to print this whole value. And let's see the output. We didn't finish the training loop yet. I just want to show you how many values are true and false. Yeah, perfect. So now it's the first line printed for us how many values. So the first value is true, is false, true, false, true, false, true. Okay, which means that we have 16 outputs and we have 16 labels, so we are comparing them, which are true and which are false. And .sum.item brings us in total, we have 6 true, 1, 2, 3, 4, 5, 6. So we have in total 6 values are true. So this is the accuracy. 6 values out of what? Out of the whole batch and out of the whole amount of the data for this batch. Okay, so let's clear these prints and clear these breaks, and after that we're gonna do the same as the loss. So total accuracy train is equal to is plus equal train underscore accuracy. So we are going to add the accuracy, and then we are going to tell our optimizer, please take a step and change those weights, because we are in the back propagation now. We are in the back propagation, which means we want to optimize the weights. Great. Now that's it for the training part. Now what else? Like we can go out of this loop now, and we are still in the epoch. We want to do the validation part. So we start with torch.nograd. This is the same way we have done last lab, which means that use the model, but without optimization. We are not optimizing the model now. We just want to test it. Okay, we are doing a validation process. We're gonna add another loop. So for inputs, labels in val underscore loader yeah, no, without this. Okay, and then we will do the same process. Outputs equal model of inputs. Now we are expecting that the model would be somehow better because it's already optimized its weights, but not necessarily, okay? So, but it of course, it gets better throughout the training. And then we're gonna have val underscore loss equal the loss function, because we want to calculate the validation loss now, outputs, comma, labels, and then we are going to do total underscore loss underscore validation is plus equal val underscore loss dot item. Okay, and then validation accuracy is equal to the same thing we have done here, so we can copy this for simplicity, and then total underscore accuracy underscore validation is plus equal val accuracy. Great. Now we don't need optimizer zero grad, we don't need backward propagation, and we don't need step. We are just testing the model and seeing the result. That's all. Okay? Okay, that's all. Now, regarding the next part is inside this loop, we didn't use these. You remember? We didn't use these. Okay? So we're going to use them now. So we're going to take this one, total loss train dot append. So what are we going to append? The loss of the training. So which is total loss train append. But let's put round because the loss is going to be a bit high and this is expected, no problem. So let's do round of the total loss train divided by 1000 and comma 4 values only after the decimal point. Okay, and we're gonna take this line, paste, we're gonna have total loss validation, and instead of total loss train we're gonna have total loss val here. Okay, then we're gonna do the same with the accuracy. So here is the accuracy, we can take it like that, and we can change total accuracy train, and here we are going to take total accuracy training. Now accuracy, we want to display it in percentage, so it's better that we divide it by 100. No, sorry, we want a percentage, so we want how many was true out of the total amount of data. So we can put total accuracy training, we're gonna divide it by the train underscore data set, train underscore data set dot underscore len. You remember the len function? It gives us the amount, the number of images we have inside this training. So total number of images, we are calculating the number of correct ones divided by the total number of images we have inside the training. So divide by that, and then we can take all of this, you see all of this, multiplied by 100 to get a percentage, and round it to 4 as well. And that's it for here. Now we're gonna do the same part for the validation. So total accuracy validation, we're gonna change this into total accuracy validation here. And instead of train data set, we're gonna have val data set. And that's all. Okay. Now, after that, we want to print these values. Okay, so we want to print and see the things like in TensorFlow. So let's print it in a neat and nice way. So print f, and let's put it in 3 quotes, and we can put, for simplicity, and we can put epoch of which one. So epoch of epoch plus 1, because it starts from 0, so we want it in a neat way, out of number of epochs. Okay, and we're gonna have comma train loss, maybe, yeah, train loss. Now you can put this like whatever shape you want, but I'm trying to make it simple and neat. Round. Okay, now training loss, we're gonna take the same training loss we have here, total loss train, and we're gonna print it. And then after that, we are going to have train accuracy, which is gonna be the total accuracy for training all of that part, and then we are going to have enter, and the validation loss, so validation loss is going to be this one, total val loss, and the validation accuracy, which is going to be total accuracy validation, that one. This is a printing statement. It's optional at the end, but it's better so that you see the performance of the model. Okay, and that's all. So we can print it now, and we can start the training process now, and let's see. So this step may take some time, okay, and let's see. Now, this part, I hope this is clearly now the difference. I hope this difference is clear between total accuracy train and total loss train, and I mean these values and these lists. Okay, so these lists will be used for plotting, but these values are going to be used for visualization and going to be used as well to calculate the loss and accuracy after each epoch and all of that things. Okay, so let's see. Hope everything is going without any errors. The training will take time, so I'm going to see only the first epoch, and then I can stop the video and continue again after it finishes training to avoid wasting time. Okay, so you can leave it, no problem. It will take some time. So I'm having T4 here. If you have better GPU, it may be faster. If you have Collab Pro, of course you can choose different GPUs. Like here you have other ones if you having Collab Pro, but it's not necessarily you go because they are paid. Save, we're not gonna change. Okay, perfect. So everything is going fine. Epoch 1 started by training loss of 33%. 31%, 0.31, 81% of train accuracy, 0.0473, and 87 for the validation stuff. So I'm going to stop the video now, and we're going to continue after it finishes training. So the training is done, and we are back. So let's continue now. So the training looks good as it reached train accuracy of 99.62%, validation accuracy of 96.32%. And the loss is extremely low, so the model looks very good. So let's test now. We have a testing data. You remember we divide our data set into train validation tests. So let's do the testing. So we start with torch.nograd. Now we explained that before, which means that we are not going to change the model weights. So total underscore loss underscore test equals 0. And then total underscore accuracy underscore test equals 0 as well. And we are going to have 4 inputs, comma labels in test underscore loader. So it's the same way we are doing the validation, but the validation was in a loop, but inside the training loop, but now this is separate. So predictions or outputs or whatever you want to call it is model of inputs, and we are going to calculate the accuracy same way we were doing here. So like that one, we can copy it. It's predictions, and we are going to have also the loss, so we can calculate the loss as well if you want. So this is the part that calculates the loss. I'm gonna change it slightly. So we're gonna have total loss test is, and let's call this as test loss, and it's called predictions, not outputs, and that's all. So great, now we can proceed, and that's it. We can print f of accuracy score is, we can print the accuracy we got. So we're gonna do the same as what we did for the accuracy here. Okay, so yeah, here, that's the one. So we're gonna put the round things and calculate the percentage, but instead we're gonna have total accuracy test divide by the test. Now I'm a bit fast here, but because you already know all these steps now. And then we're gonna have also the loss, and loss is Loss means the error. So we're going to have also the loss rounded the same way we were rounding it here. And like that, instead of total loss train, we're going to have total loss test. And that's it. So let's try to run and see if we have any issues. And let's see, this may take some time depending on the amount of the data. And okay, accuracy is 0. So I think we're calculating the accuracy somehow wrong. Labels.sum.items, so predictions equal labels. So we seem to have some problem, okay, because accuracy doesn't make sense to be 0. How are we calculating the accuracy? So let's print ACC, okay, let's debug this together. Print ACC is 2. So yeah, there is a problem here. So yeah, accuracy. Okay, we are not adding to the total accuracy test here, okay? So total accuracy test needs to be like that, ACC. And now it's supposed to give us some valid number. We need to keep adding to accuracy after each batch. So that's the point. Yes, perfect. Now we have the accuracy is around 96%, almost 96%, and the loss is 0.0267. So the model looks really good. Now we can plot the training progress. You remember we had these 4 lists so that we can plot the training progress. So let's plot it. Fig, AXS is equal to plt.subplots. We are creating subplots of number of rows equal 1, number of columns equal 2. Why? Because we want to visualize 2 plots for training, for accuracy and for loss, and the plots are beside each other, so in 2 columns and in 1 row. And the figure size is, now let's put any size, it doesn't matter, let's put 15 by 5, and let's fix the first plot. So the first plot is AXS of 0 dot plot. Now we need to plot the total loss training. Okay, so we're gonna take the total loss train, the list of the total loss train, and we're gonna have a label is equal to training loss. Okay, and we are going to have AXS of 0. We're gonna have another plot as well, which is the total loss of the validation, which is that one, total loss validation. And we're gonna put it here, and we're gonna put the label of validation loss, and we need to put a title to make the plot looks good. So dot set title, what's the title we're gonna set? Is training epoch, training and validation loss over epochs. Okay, this is just to make the things looks good, and we're gonna have some labels on the axis. So axis of 0 dot set x label. It's called set x label, I believe. Yeah, set x label, and it's gonna be epochs, and we're gonna have also set y label, which is gonna be, because the x represents the epochs and the y represents the loss. Okay, and then AXS.legend. Okay, great. Now we're gonna do the same but for accuracy. Now this is, but it's gonna be for axis 1. So we're gonna change these to axis 1, and here it's gonna be accuracy, and this accuracy, I'm gonna put this here, training and validation accuracy over epochs, but instead of train loss, it's gonna be train accuracy. So it's gonna be this one, train accuracy, training plot. The first one for the training accuracy, and the second one for the validation of the accuracy validation. Oh, sorry, not here. It's supposed to be here. And yeah, that's it. Now let's do plt.show, and let's see the output. figure set n underscore rows. Yeah, it's supposed to be n rows only and n columns only without underscores. Okay, no attribute legend. Okay, so we can, yeah, axis of 0 legend. This is to make the things looks neat. Okay, and here gonna put 1. And let's see the output. Perfect, here is the output. So you can see that the output is, we can see if there is an overfitting or not. So you can see between the training and validation, there is some sort of overfitting. Okay, it's, yeah, there's somehow a sort of overfitting now. And here also a very small outfitting in the loss. Overfitting. So you can change in the model, you can play with the model, add drop out layers, you can increase the epochs, you can reduce the complexity of the model, and try multiple things and see the results yourself. Now let's go into another interesting part, which is the inference. What if we want to use the model on a separate image from the internet? The model may not be very good, okay, even though we have a high accuracy and low loss, but there is some sort of overfitting, so it's fine if the model didn't predict good. But we want to know if we can predict a model. So I opened this one. I searched for some cat faces. So again, we can take that one if you want, and we can try it. So let's save the image and let's save it in downloads, and we can go and upload the image here. I'm gonna show you how we can do an inference. So let's take this one here. Okay, perfect. Now first thing we need to know is to read the image. Read image. Then second thing is to transform the image into our using the transform object we created. And then we can give the image model, predict through the model. The model will give us some value, and this value should be inverse transform by the label encoder. Now we can create this inside the function if you want. So def inference. Or let's say predict image, maybe predict image, and it takes image. Okay. Now what should we do? First of all, we need to know how to read the image. So you remember, we read the image through this one. Okay, so we can read the image here. We can give the path of the image. So this one, we can copy the path of it and put it here. Now we have read the image. Now I'm not sure if it can read this format, but let's see. If it doesn't, we can bring another image, no problem. And then we're gonna have to do the transform part. So we can copy it directly, image self.transform, and move it to device. Okay, image self.transform, we can remove self because we have already the transform object, and move it to device. And we can give it to the model, model.predict, or no, without predict here, model directly image, and let's print the image size as well. Dot shape and model of image, and then return. Okay, let's call this output equal model, and then we can return the output. Let's see. Yeah, here this path, it should be given image underscore path, and we can call this image underscore path, and then we run predict image, and we give the path as that one, and see the output. And so it cannot read this type of images, so no problem, we can get another one. So let's see if it can predict that one, or maybe that one. Okay, so save image and save, and we can go here, upload. This is a JPG image. Yeah, upload, and perfect. Now we got that one, copy path, and we're gonna put it here. Let's see if it can predict that one. Okay, we have a problem with the shape. Okay, so no problem. We got the image as 328 by 128. Now we need one more dimension, which is corresponds to the batch size. Okay, so what if we tried the squeeze function? So it's print image dot squeeze. Now I'm trying this with you. So let's see, dot shape. If we squeezed the image, will it fix the issue? No. So it's unsqueeze, I believe. It's one of them. Yeah. So unsqueeze makes it having the batch size thing. So we need to put the unsqueeze part in here. The model expects batches of image. So we need to tell the model that we are only having one image in like the batch contains only one image. So, and that's all. I believe after that it's gonna work. So we are giving it unsqueeze of 0, and then let's tell it to get the output, and perfect. Now we have an output, okay, but we need the maximum one. So it's ranked 0, 1, 2. So we need the maximum. So we're gonna use the same thing we have used here, torch.argmax of the output. Okay, so we're gonna return torch.argmax of the output. So the output is 2. Now what does 2 means? So let's put it here in a nice way. Output equal this one. And what do we want? We want the label encoder. I think it was with underscore, label encoder dot inverse transform of the output. Let's see. And it predicted for us. Okay, we need to take it out from the memory first. So we're gonna use dot item. It expects a list, so we're gonna put like that. Okay. And it gave us wild. It's, even though it's a cat. So no problem. I told you the model is not very good. There is some sort of overfitting, but you can try again and rerun the model again and see. Now, if you see the outputs, okay, so we can print output, and you see here the output, even though it's wild, but you can see that this class is the second highest and this class is the second highest, the lowest. So this is the top, second one, and third one. So it's not a very good model, but this is the way of doing the inference, okay? And I will attach the link of these images, okay? I have also here a GIF that represents the convolution animation, and here for the pooling as well. I will attach these as well in the description if you want to have a look on them. These are not from me, these are from separate links on the internet. I'll put all the links inside the description, and also you'll find the link of the full notebook explained very well inside the description on GitHub. If you have any questions or anything is not clear, feel free to write a comment, and I will reply to this comment as soon as possible. Thank you, and I hope you enjoyed. Hello everyone, and welcome back to the series of PyTorch exercises. In this lecture, we are going to see how we can fine-tune a pre-trained model. So the steps are almost similar to the previous lecture, which was the image classification. Here we will also do an image classification, but we will use a pre-trained model. What does a pre-trained model means? Well, a pre-trained model means a model that was already trained on several tasks, and we are taking that model, doing a slight modification at the final layer of that model so that the model saves and uses its old knowledge in order to solve our current problem, okay? So we will not be building a model from scratch. We will be getting a model that is having already some knowledge, and we will be, it's called the transfer learning, not fine-tuning. We will be doing transfer learning so that we transfer the knowledge of our dataset into that model. Okay, great. So this is our dataset that we are going to use. It's called bean leaf lesions classification, and it contains 3 classes. healthy angular leaf spot and bean rust. And it has two files, train and validation. So let's go ahead and download our dataset. So we will, first of all, let's connect into a GPU, T4 GPU, and let's start doing our installation of Open Datasets library, --quite, and we will import Open Datasets as OD, and we will do od.download. Okay, great. So now it will connect to the GPU first, and then it will ask us for the credentials. Let's give it a moment. Yeah, so let's use our username, and I'll paste my password. Okay, so looks fine. The dataset is 155 megabytes. And this is something that we will learn here, okay? That the dataset is somehow a little bit small. That's why we are using transfer learning, because transfer learning is a suitable option for smaller dataset where you don't have a lot of labeled data. Okay, now let's start by our imports. So we first need to import PyTorch. So import torch, and we'll also need to import NN from PyTorch, as this will help us to use the layers. There is some auto-completion here as well, but let's use our effort here better. Import Adam as our optimizer. We'll also need to import transforms, and it will be used to pre-process our data. So import torch vision.transforms. Not all of that, so let's dot transforms. Sorry about that, it's a typo. And we will import something called transforms from that one. And we'll also need from torch, sorry about that, from torch dot, we'll need the data loader, but we will not need them nest, so data loader is fine. We will also use something called dataset, and we're gonna need as well, I believe we will need models. So from torch vision, torch, not sure what's happening with me today, import from torch vision, import models. PyTorch has a lot of pre-trained models that are already built inside PyTorch library. So if we go here and search for that, models and pre-trained weights, so you can see here all the information that we are having about all the models available. So there is a way, yes, here are all the models available about the pre-trained models for images. So you can use any of them. For this lecture, I believe we'll use GoogleNet, okay, that one. So let's start, okay, let's continue. And from Torch Vision models, we will also need from sklearn.preprocessing import label encoder, and this will be used for converting the string classes, because you see here that they are string, so we need to convert them into integers or encode them. So we'll use the label encoder. And we're gonna need as well to import matplotlib.pyplot as PLT, and this will be used for plotting. From PIL import image, this will be used for reading the images. And we'll use import pandas as PD. Pandas is already a well-known one. And import numpy as MP just in case. And import OS, where it will allow us to access our dataset on the directory here. Okay. So it looks like all the imports are working fine. And let's put one thing else to verify that we have GPU. So yeah, great. We have the auto completion. So device is CUDA. If torch.CUDA is available, else CPU, which means that we need to check the available device before we proceed, and we should expect CUDA, and that's fine because we are connected to the GPU here, which is great. Okay, now let's start with reading our dataset. So let's check our dataset. So we have the dataset is already prepared for us in a good way. So we don't need to go and read each image separately, but each image is available here in train and val. So let's try loading this. So we can write train df is equal to pd.read csv. And here we can take the path of that one, just for simplicity. We'll take this one, paste it here. And we're going to do the same for val df, which is pd.read csv. And we're going to take that one. Great. So let's check the data shape. So train df.head. Let's check first the data frame that we have. Great. So it contains image file and category. Okay, so looks like we are good. We don't need to convert category into from string to integer, as it is already converted, and that's a lucky case. Actually, datasets are not that clean. We need to do some work, but our dataset luckily is clean. So we have the category and we have the image file. So let's check the possible categories that we are having. So category and dot unique, should be brackets, 012, which stands for healthy angular leaf spot and bean rust. I believe that this is the case. Great. So okay, let's proceed now. I think we can proceed safely without any issues. Let's check how many data we have. So print the train underscore df.shape and val.shape, which means that it will print us the number of rows and columns in each one. Okay, so let's see. We have 1000 row for training and 133 for testing, for validation. Okay, looks fine. So we can check also the class, the class distribution. So we can see our classes, some data pre-processing. So we can check train df dot of category, because we have category dot value underscore counts. Yes, that's the one. And let's print only that one. Great. So the data set is balanced. That's a good thing as well. So the only challenge you can see here is that the data set is not having few amount of images. This is considered a very few amount of images because you have 3 classes. Each class is around 350 images, which is a little bit small amount. And in this case, we usually go to transfer learning, where we use a pre-trained model and train this model on our data set. Or in this case, it will not be called train, but we will do a transfer learning, which means transfer the knowledge into that data set. Okay, great. Now let's proceed into using this data. Okay, so we have 2 options. We either add these 2 data frames together and we split them again, and in the notebook you will find that I'm doing this, or we can skip this part and we can directly use our data set as it is, as there is no need to change it again or to split it again. You have both options. In this video I'll be going through it without any extra splitting. We will use the same splitting as the original data set, and inside the notebook that you will find in the description, I'm doing an extra split. Okay, great. So let's now create a transform function. So what is a transform function? Now transform function is a transform object is an object that we are planning to use that will help us pre-process the images. So to make sure that we are giving the model images, all of them are the same size and the same type, we will use this one. So we'll use transforms object that we have got dot compose, and we will start using putting some features here. So we'll use transforms. Sorry, let's write it better because it doesn't make sense that we always use that. Resize. So we are going to how can I close that thing that auto completes? Okay. Okay, anyway, so I don't think, yeah, AI assistant. Yeah, let's be a little bit old. This way will be easier for us to understand what's happening. Okay, so we're gonna make all the images 128 by 128. That would be much better, and we'll make the images in one size. We can increase the size of the images, of course, but the more you increase the size, it means more pixels, and it will be slower in processing and slower in training. Remember, we just need to illustrate an idea here, and you can try it later, but we have somehow limited GPU, not a very big one, and we have also something that may get time out. So better we make things fast here as we are learning. If you are using your local machine and you are having a GPU, feel free to try other stuff. Okay, so transforms dot to tensor, which means that we need to convert them from float into PyTorch tensors. Okay, and we'll use the last one, which is convert. Now, image the type. The type, and we'll convert it into torch.float. Yeah, that's it. Okay, what are we doing here? So let's go again through all of this. Transforms.resize makes the image, all the images into a certain size. Transforms.tensor converts the type into a tensor instead of a normal array or list into PyTorch tensor. Now, what is inside this tensor? We have a bunch of numbers. What is the data type of these numbers? This is where we convert them into floating point here. So we make sure they are a floating point, but torch float, not a normal float. Remember that PyTorch is a whole ecosystem, and it's always better to convert everything you are having into PyTorch stuff so that it could be easier for you. Okay, great. So now let's create our custom dataset. We'll call it custom image dataset. And we are going to define our constructor here. So self, it takes our data frame, because this is custom. We can create this as however we would like, okay? So it takes a data frame because the data is already provided, the path and the classes are in data frames. And we are going to give it a transform equal none, which is a transform object. Or maybe not none, because the transform will be needed. Let's put only transform. And we will do some basic stuff. We will assign self.dataFrame into our data frame. And we will assign self.transform equal transform. And we will also assign self.labels equal torch.tensor for the data frame, as it is already prepared for us for category. And we will make sure that all of this will be moved to device. Okay, you remember our device, the device which we declared here was CUDA if the CUDA is available. If it's not available, it will automatically take the CPU. So this code should work on both GPUs and CPUs. However, for CPU, you should expect some delays. Okay, we will define another function which is called len, as this function is necessary. So remember one thing, okay? We are inheriting from originally class called dataset. And this is an original class that we are inheriting from, and we are overwriting some functions inside this class to match our dataset or to match the structure of our dataset. That's why it's things in PyTorch you may feel that they are a bit difficult, but it's not difficult. The thing is that PyTorch requires somehow more customization, and this customization in some cases is really important because it allows you to use any type of datasets, in any format or any structure. You can have full control on that. And here we will return the len. So the len is actually since the len is how many rows inside the data frame, or how many images. How many images usually translates in our case into how many rows inside the data frame. So self.dataframe.shape of 0, because shape is having two items, 0 and 1, and 0 is the number of rows and then the number of columns. Okay, great. Now we are going to do the second one, which is get item, another function that we need to overwrite. So it will take, this function will require a little bit of work here. So we will start by image path is equal to self.dataframe.iLog. If we need a certain path, okay, we need to provide the index of the path that we will require. So index, or maybe let's get it even smaller, loc of specific row that we desire, and 0, which means the image. Then we will get the label of that image, which is self.labels of idx, which is our index. So if we have a certain index and we want to get the item of that specific index, we will do self.dataframe.iLoc. iLoc allows us to retrieve a certain element inside the data frame, which is by index, row, row, column, which means that index means the image, and column means the first column of the image path, okay? And index means a specific index inside this data frame. Label is self.labels, because we already declared labels here as a torch.tensor. So we are treating it like an array or a list, self.labels of that specific index. So it's really straightforward. And we can read the image now, because we are reading the image location. We don't have yet the image. So we'll use the image that we imported from PIL, and we'll use .open. And inside this, we will put the image path that we got here. Okay, it will be a string, so we will use it here. If you stand here, it will tell you that FP is expected to be a string. So it will be somewhere here, but FP is expected to be a string, and the mode is reading, which means it reads that image. If self.transform, we already will provide a transform class. So if self.transform, so which means that if we are having something as transform, we will do the transformation on the image. So we'll use self.transform image. And we will also want to do normalization on that image. So we will divide it by 255.0, which means that we are doing normalization, as each pixel inside that image is having a value from 0 to 255. So we divide by the highest value to make sure that the image is coming as not, for example, not a bigger numbers, as a smaller numbers. And we will make sure our labels are already in the device, which is the CUDA or GPU, and we'll make sure to move this one as well to device. Okay, and that's all. We will need to return the image and our label. Okay, great. Let's run. Okay, looks fine. Let's try now to declare or create two custom data sets from our data frames. So the first one will be train data set equal custom image data set, and it takes, remember what it takes, a data frame equal train underscore df, and it takes transform. Now it's telling you that it takes a transform, and transform is equal to what? Our transform object, which is that one. Okay, And we are going to do the same. We'll copy paste it for faster writing, and we'll have val data frame, and here we will write val df. Now the transform object is the same object for both of them, and that's of course obvious because we will need both of them to have the same specifications. Let's run. Do we have any issues? Okay, looks good. Great. Now, before we proceed, there is a part that I like always to do, is to see our data set. So let's maybe see a part of the data set. This is optional, okay? It doesn't matter. You can just go simply here and open this folder or any folder and see the image. So maybe you can download it and see it. I don't know if you can open it here. Yeah, you can open it here as well, and you can see it. But I would love to see a couple of images here. That's, again, that's an optional part. If you want to skip it, you can skip it. Number of rows is 3, and number of columns is 3. So we want a grid or a matrix that having a 3 by 3 elements, which means 9 elements in total. And each element of them will be a random image from our dataset. So we will create a plot as a figure and axis array as plt.subplots number of rows multiplied by, not multiplied, but number of columns. And we'll take 4 row in range n rows because we will loop through each row and we will loop also through each column. Okay, I think we're good. Now we can take a random image. So we will take a random image from the training data set, and we will choose a random index for that image. So rand int, and we are going to specify the random index between 0 and the len of the image, which is train dataset dot underscore len. Remember the len function, which we have got here. So what we are doing here basically is that, I think there is a typo, yeah. What we are doing here is getting an index from train dataset. You can specify a number here, but I'm doing the number to be a random number. So I'm initializing a random number, and the random number should have the length between 0 till, or a range between 0 until the length or the number of rows of our dataset. Okay, and rand int of 0 and .cpu, because we need to transfer it to CPU because we are not doing any training. We want to do some visualizations only, and we want to display our lovely image here, and the image should have the length of, the image is normalized, so we should return it back into our original size, because we already divided by 255 and we are using the custom image dataset inside the train dataset. So we want to return it back, and we want to do .squeeze because we may have some issues related to the shape because of the batch size. So we want only one image, and we'll use .premute to modify our shapes into 1 to 0. Again, this is optional part. There is millions of ways to do visualization, but that's how I'm doing it. So if you don't want to do visualization, it's fine. Axis is off. We don't want any axis. And then we will display our plot, so as a tight layout. And then we will do the show. Now let's see if we have anything. It takes some time. Int object is not subscriptable. So I think we don't need that. Int object has no attribute CPU. So CPU is not supposed to be here. Actually, this 0 is supposed to be outside because this is from the train dataset. So I think that will be fine. No such file or directory for that one. Okay, that's It's a little bit strange. So let's check what is happening here. Train data set for len. Not sure, maybe something with the randomization. It's choosing already a train. Okay, so you see the issue here is our path. Okay, so the path here is train, directly train. However, the path here, when we copied it, there is part called content. So we need to add a content part into our path. Okay, so we will make sure that the path is complete, because the path here is coming from starting from train. So we need to change the path inside the two data frames into the full path. Okay, okay, not an issue. So we will copy all of that until here, and we will need to add it. So we will do data of train underscore df is equal to, we'll fix the path. So train df, of image file is equal to, we are going to take our path and we'll add it into the older path, which is that one. And we will do the same with the validation data. That's a mistake, so it's not a big deal. And I think now we can proceed. So we can run all of them again and check now. So content is that one. Because we forgot to put an extra slash here. So we can run this one again only, and that one. Now it should be fine. Okay, now there's a new error, which is dot premute. So dot premute is something that is strange. I'm not sure why this is happening. Dot premute is supposed to set the shapes. So let's remove it. Maybe it doesn't require setting the shapes. Invalid shape for 328, 128. So we'll have our image multiplied by 255, and we have dot squeeze, and we have dot premute. So it's saying that tensor has no attribute premute. Okay, so it seems like a typo, so we can put permute. Okay, great. So now we are having all our images here that are fine. If you run this cell another one more time, you will get a different images because it's random, and that's why we are using random initialization. So we are good to go. So it seems that the images are clear and maybe not the best, but they are good. So we can proceed. Now let's move to the interesting part where we will start using the model. So we'll set our learning rate equal to 1e minus 3, and we are going to set also the batch size to 4, maybe 4, yeah, would be fine. Epochs to 15, I think 15 would be good. Okay, and then we will we'll create a train loader so that we can do the training with batches. Data loader, and it takes train data set and takes the batch size that we wrote, which is batch size, and it also takes the shuffle equal true because we want to shuffle our images. And we'll do the same with the val data loader. So val data loader, and it takes the val, and everything else is the same. So it seems data loader is not defined, even though we got it here. It needs, it's a typo as well. The L is capital, so that's not a problem. Great. Now, oh, sorry. Oh yeah, it's on. Okay. Okay, all good. Now we need to bring our model. So we have a couple of pre-trained models here. We'll use GoogleNet. How we can use GoogleNet? It's very simple and straightforward. So we'll write GoogleNet model is equal to models that we have imported from PyTorch, from Torch Vision. And you can see here all the available models. So we want Google linet, that's the one. And we'll take its default weights. Okay, now it's downloading. Okay, it was fast. The model is not very big, it's around 50 megabytes, which is good. Okay, now we can proceed and do the following. For param in Google net underscore model dot parameters, and we are going to do param dot requires grad equal true. As you know, the model is having a trained weights already. So we are starting to teach the model from these trained weights. The model is having some knowledge, and we are expecting that the learning part wouldn't take much time and wouldn't require so much data. So we will set this, which means that we are telling the model that allow your parameters to learn again, or allow your weights to learn again. But the difference in this case is that instead of starting from random weights, no, it's starting from a weights that is already having some knowledge, but not the best knowledge for us, let's say. And this is where we are going to do the rest of the part. Now, there is a different way of doing this, is that we set this into false, which means that freeze all the weights that the original model is having, and we add more layers into it, and we train these layers. However, we will not do that. We will allow the model to learn with all its parameters again, okay? Okay, now we will run this, and we are good. Now we want to check the last layer, dot fc. So .fc will give us Google Linet. So I think this is a typo, Google Linet model. So .fc, it will give us the last linear layer. So the model is expecting to predict 1000 class, but that's not the case, okay? We want only 3 classes. So we need to change that, okay? Okay. Great. Now we can do one thing, is to change the length of the parameters. So we need to check how many classes we want. We can check it, of course, like that. We can check the length of data, train df dot of category dot unique, which means that we will check how many unique value we are having in num classes. Maybe we can print it here. And we have 3, so we will change our model in our last layer, which is that one. Oh, sorry. We'll change that one into torch.nn.linear, because it's already a linear layer. And we will put our original number of features, which is the 1024 dot in features, and we'll put the number of classes, and then we can put it here again to show the new layer. Great, now it's fixed, no issues. Now we can do one thing. We can again set this into false and only train this one. Or we can, which is a completely transfer learning, or we can retrain the whole model again, okay? But, okay, let's try both, okay? Let's try first doing the whole training, and then we can try the other one. Okay, great. Now, we need to do one little thing, which is moving this model to CUDA device, because we have our inputs and outputs on the CUDA device. So we have moved the model. So, okay, let's close this, or maybe we can keep it, no issues. Let's close it for cleaner output and having things a little bit optimized. Okay, hide it better. Great. Now let's proceed with the training loop. But before we go to the training loop, we need to define our loss. So we will define our loss part. So maybe we can write critation or loss. So maybe we can write loss is equal to, or loss fun is equal to nn dot We'll use cross entropy because cross entropy is used for multi-class classification. And we are going to use Adam optimizer as we mentioned in the beginning of this lecture. Adam, and we need to provide to the Adam optimizer the Google net parameters. So dot parameters, and we will provide the learning rate as our LR. Then we will start the total, we'll start the training loop, but we will first need to define a total loss, which is also will be used to get the cost. So total loss train plot is similar to what we have done before. Is equal like that, and total accuracy train plots. By the way, we will not be using any validation data. We will use the validation data as testing data at the end for epoch in range epochs, and we will start creating a default variables for total accuracy train, and this will be increasing through time, and we'll do the same for loss. And then we will take our inputs and labels in train data loader, because now we will loop through the batch level. Yeah, epochs is not defined, so maybe we defined it like that before. Yes. So train data loader, I think there is some mistake here, so let me check. Train loader only, not train data loader. Okay. Okay, now we will reset our optimizer. So optimizer.0 grad. And we will allow the model to do a prediction. Google Net model for inputs. Then we will do train loss is equal to loss fun. Loss fun of what? We will do the loss fun of output. So we will do the loss between the output and the original labels, the output of the model and the original label, its outputs. And then we will do the loss calculation. So total underscore loss underscore train is plus equal train loss dot item. So we are adding this to the total loss because we need to calculate the cost and the final loss for each batch. And then we will do train underscore loss dot backward to allow the model to do backward propagation. Train accuracy is equal to torch.argmax. So we'll check the accuracy of outputs, comma, access equal 1, equal labels, and we're gonna put all of that into brackets because we want to check if our original labels is equal to the model outputs or not. And we will put dot sum to sum how many are true and how many are false, and dot item to get the certain value. And then we will add it into our accuracy is plus equal train ACC, which is train accuracy, and we'll do optimizer.step to allow the optimizer to do its job. Then we will go back a little bit and we will put this total loss and total accuracy lists will be used for plotting at the end. So total loss train plot, yes, that one, let's copy paste it easier. Dot append. What are we going to append? We want to append round of total underscore loss underscore train. We want to append the total loss for training, and we want to divide it by 1000 because it will be very high, could be very high number. So we divide it by 1000 better, and we round it to 4 decimal values. And we're gonna do the same for the accuracy. Let's change that into here, and we will do the append, but instead of this we will do total ACC train, and instead of dividing it to 1000, we will divide it by train underscore data set dot len, so that we divide it by how many is, it's like saying how many are true total out of all the data set that we are having. Okay, and we want to convert it to percentage, so we multiply it by 100, and that's all. So maybe we can put a print statement. So print the number of epochs. So maybe we can put an F here, epoch of epoch plus 1, because it will start from 0. And we are going to divide it by, or say out of, maybe, or like that, not divided, but out of number of epochs. And we will write our training loss, train loss, as this thing. And we will write also train accuracy as this one. Okay, and that's all. Actually, we can add more stuff, but yeah, maybe we can add a percentage sign here, because it will be a percentage, and I think we are good to go. So let's start the training. Let's see, our training is working. So if it runs till the first print, will be very good, and then it will be a matter of time, or just need to wait. Great, looks good. So the model started training. This is gonna take a while, so I'll stop the video now, and maybe we can proceed after the training is done. Okay, so we are good. The training is done, and these are the values we have got. So maybe we can do the testing now. So we'll start with torch.no_grad, and we will put our total loss test. So we'll define the same way we did in the last lecture, the testing loss and the total accuracy test as 0. And then we are going to do for index, comma input. Maybe we can put this like that, because we want the index, or maybe no need for the index. So for input, comma labels, enumerate test, or sorry, we will not use the enumerate, in test loader. So in test data loader, or I think it was named test loader only. No, let's get the exact name. I always forgot. Val loader. Okay. In val loader, no need for this. And then we are going to put prediction is equal to Google net underscore model of input. And then we will calculate the accuracy same way we did before. So torch.arg max for prediction, comma axis equal 1. And we are going to put is equal labels to see how many are correct. Dot sum and dot item. And then we'll do the total accuracy test is plus equal accuracy. Maybe we can ignore the loss. It's not a problem. So let's try to see. So we can ignore the loss. So it's done. Let's see how much accuracy we have. So the accuracy will be print round. We'll do the same as the training. Okay, so round of total underscore accuracy underscore test divide by the test underscore data set dot len multiplied by 100 and round it by 2. Okay, sorry, not test dataset, it will be val dataset. Yes, perfect. Now let's print this and see how much accuracy we got. 86%, which is great. Okay, so 86% with a very few amount of data, that's a very good work. However, can we do better? So the thing is that let's try pure transfer learning. So let's try leaving this as false. Okay, so maybe we can copy this down. So let's write here transfer learning. There is a slight difference between this and the notebook. So if you feel that there is a big something that you are kind of lost, feel free to ask in the comments. So now instead of having true, we will write as false. Okay, and then we will take the same layer, that one, and we will do the following. So let's load the model again. So let's get a new instance of the model first. So let's put that one down. So let's get a total new model. Okay, and then requires grad is false. We change the number of parameters, and the last layer only we'll put it as requires grad is true. Okay, and that's all. Rest are the same. So let's run. Let's see. Good, it's working. Now it's just a matter of copy pasting. So we can copy the whole training loop now and run it again here. And let's copy the testing part as well and run it again here. Okay, so there is some mistake. Should be the same. Wait, input type float tensor and float tensor CUDA. So I think there is something we forgot to move it to device. Yes, we forgot to move it to device. So we will need to write this part, net model dot to device. Because this is the new model now, okay? We are not using the same model. The old model that we trained is fine, done, but now we're using a total new model, okay? So let's run. Oh, sorry, I added something wrong here. Okay, so it's done, and the accuracy part, yeah, we forgot to print it. So let's take the printing part, copy paste it here, and let's see. So the accuracy is 56%, and before that was 86%. So the thing is that this could be for two reasons. We are doing in the second part, we are doing the fine tuning or the transfer learning only on the last layer. This could be good in some cases, but in other cases it could be worse because like here, we didn't add any extra layer. We are changing in the model knowledge partially. So we changed in the last linear layer. However, in some cases, we add extra layer and it works better because we will have more parameters to optimize and the model will preserve its knowledge. However, in the first thing we did and we tried, we didn't preserve the knowledge. However, we retrained the model again, but we started from its own knowledge or its current knowledge. So we told the model, okay, you learn everything on your own. However, in the second part, we told the model, okay, only this specific part can learn whatever it wants, but you should stay the same. And this specific part was a major part inside the model itself, not a part that we have added already. So you can try adding more layers and do the requires grad is false for the model itself and add more layers and make them requires grad equal true, or you can go with this part. I would personally go with that part where I will allow the whole model to adapt on my own dataset. Thank you very much. If anything is not clear, just please ask in the comments, and don't forget to like and subscribe if you like the content. Thank you. Welcome back to the PyTorch series of tutorials. So in this lab, we are going to build audio classification example. So through Google Colab as well. And we are going to use this dataset, Quran recitations for audio classification. So this is a set of audiobooks, it's a set of audio files for different recitations by different people for the Quran. Quran is the holy book for of Islam religion. So we are going to use this data set, and it consists of multiple wave files, as you can see here, and the class, which have multiple people who have these recitations. So we are going to start first by downloading our dataset. So we have started a collab file. We have connected to GPU, T4 Tesla GPU, because we are going to need a GPU definitely here. So now we can start by downloading our dataset. So we are going to do as usual part, which is pip install open datasets, and then we are going to import it. Import open datasets as OD, and then od.download, and we are going to take this, the link of this data, put it here, and now it will ask for the password. So let me copy it. I already created a video. I'll put it in the description on how to download the dataset directly from Kaggle. So I'll write my username and the key or the password, and the dataset is downloading. So this is gonna take a few seconds. Okay, great. Now we have our dataset downloaded. Now we can start doing our imports. So first of all, we are going to import Torch, obviously. And then we are going to take from Torch import NN for the neural network layers. And we're going also to use torch.optim import Adam as our optimizer. We're going to import LibRusa. This is a library that will be used for audio processing. We are going also to need some other stuff from Torch as well. So from torch.utils.data import dataset and data loader. We are going also to import from sklearn.preprocessing import label encoder, because we are going to need this for encoding the classes because they are strings. Import matplot library .pyplot as PLT. We can use this for visualizations. We are going also to import pandas as PD, and we are going to import numpy as NP. These are some basic stuff. We are going also to import OS. We are going to import time as well. And finally, we are going to import this from skimage.transform import resize. And we will see how we will use this. And I believe that's all. Let's set also the device. These are things that we do every lab. So, or every tutorial, we need to do our imports and to set the device to CUDA. And we'll set it only if torch.cuda.is available. And if this is false, which is else, then we are going to follow the CPU. Now you can put here MPS if you have a Mac, and it will use automatically the Mac GPU. Also, one more thing to mention that, as usual, the lab is attached in the description. You can find the tutorial notebook on GitHub in the description with comments and explanations. All right, so now we have all our imports. No need to do any installations. Everything seems fine. And we already have our own data set here, Quran recitations for audio classification. We have the file path.csv and the data set, which contains all the audio files. If it's not opening immediately like that, then it means that it have a lot of files inside. And if you open this one, you have all the people here, all the people that recited the Quran, so that we will be doing the classification among them. So you can open any audio file, listen to it. They are, I'm not sure how many they are. I think they are 10 if I'm not mistaken, but we can check that through Python. Okay, so let's read the file path, and I think it will have all the information. So let's write data underscore data frame, or df, is equal to pd.read csv, and we can copy the path of that one and paste it here. Now we have the data frame that contains all the details of the data set. So I think everything is fine now. So it contains the path. Usually the audio files, you need to build this thing. So we are lucky because this data set is already prepared in a good way for us. We can access it directly, easily with this data frame. And we can also check how many classes do we have. So we can write data underscore df print, sorry, I forgot the print, data underscore df of class dot unique, and we will see how many, we'll see the classes, okay, and we want also how many of them. So we can copy them, we can put an extra line here, and then we can paste this and put len of the same thing, of only this thing. Now we have 12 classes, and these are our classes. The path of each file is already in the file path column, so no need to worry about the path. And I think everything is fine. But there is one thing to mention. This path, there is a dot in the beginning, which means that we need to edit this path to match our local path, or the path that we are working on. So this means that this path is starting only from the data set that we are having. It doesn't contain the path of your files here. So what is the path of our files? So the path of our files is starting from the word dataset, which is this one, and this one also. So we will need to edit it, okay? So we will need to put the dataset path behind this one, okay? So to have the full path here. So we will just copy the this one, copy the path of this one, and we will edit it. Okay, so how can we edit this one? So it's very easy. So data underscore df of file path is equal to our original path plus the same thing, data frame of file path. Okay. Now we need to replace the dot, so we need to remove this one. So we are going to put it str of 1 till end. Now let's print head to see how it looks like now, because now it will be clear since you will have both tables. Yes, now I think it will be clear now. So you have here, it's starting from dataset, and here it's starting from content. So which means that here you have the full path of the data. Okay, so let's try to get only maybe like the first one or something, because it will be more clear. So like that, and I'm not sure, not that way. So it should be by .iloc of 2. This is the path. Now this is the path, as I mentioned, it's a complete path. So let's delete this one and let's continue our work. Now we can investigate more on the data if you want. So we can see the data shapes. So let's print some data analysis here. Data shape is data underscore df dot shape, and print the also class distribution. So we already have this one, but we will want to print the class distribution. So let's write here class distribution, and this is going to be data underscore df of class dot value counts. And let's see here what we have. So the data set is not completely balanced, but we can say it's kind of acceptable here, because I think we can visualize it to see more. So let's try to visualize this. So let's keep like a line, an empty line here, and then we can write, we can create a plot here. So the plot, we can have it 8 by 8 maybe, and then plot should take fig size equal 8 by 8, and then we can have plt.py class counts, which is this one, and also we can give it also the labels as class underscore counts dot index. I think we're gonna need this one, not class counts dot index, and we're going to set some numeric auto pct, this one, and we are going to give it like that, so that we can have the numbers in a proper way. And then we will put plot dot title of class distribution, and then we will plot dot show. Let's see what we will get. So yes, perfect. Now we can see the data distribution here. So it's like I'll not say 100% balanced, but it's somehow acceptable. Still, there are some techniques that we can balance this by doing some data augmentation maybe, or some other techniques we can do. But we will, for this lecture, we will proceed with this data, with this amount of data, okay? Now let's start doing the data split. The data split part is where we will split our data into training, testing, and validation. So, or for making it more clear and in order, it will be train, validation, test. So let's start by making our train data, which is df dot or data underscore df dot sample. We are going to take a sample of the data for 70%, and we are going to set random state as 7. Then we are going to do the test dot sample. So we are going to take the testing as the part, not dot sample, sorry, dot drop. So I've already explained this in the previous tutorials, but just like explaining it again quickly. What we are doing here is that we are taking a sample of the data for 70%, and the rest is we are going to drop it. So the other 30% we are going to drop it, and then we will have the 30% for testing. Then we are going to do the same but with testing data, because we have, the plan is to make 70% training, 15 validation, 15 testing. So validation test dot sample, and we are going to take a sample from the test. So we need to write here frac equal, and we are going also to write here fraction equal 0.5, because we are it's a 30% already, so splitting it to 0.5 will be 15%, 15%. And random state is 7 also. And then we will take the rest, which will be test dot drop. We are going to drop from the testing data the ones we took for validation, val.index. Now it makes sense, I believe. And we are going now to visualize our data. So print train shape. Now let's see the shape of our data. And this is going to be train.shape. Let's copy this and put val.shape and test.shape, and here val, here test. Now let's see how it will look like. Great. So this is our data. So it's 70%, 15, 15. Now it makes sense. Now we can proceed because the total amount of the data we have is 6,687 audio files. All right, great. Now I think everything looks good. Now let's start going a little bit deeper and start creating our label encoder and the custom datasets. All right, so then we are going to start by having the label encoder first, because we need to change these into classes. So these names need to be encoded into numbers, okay? Okay, now let's try label encoder is equal to label encoder. And so we created an encoder instance, and then we will have class custom audio dataset. We are going to create this custom audio class. Now it will contain everything related to data processing. So it will be like before, but we will have one more function to process the audio file. Okay. Now let's first start by having the construction. So def initialize, and we will have self and the data frame. As we mentioned, it will get a data frame because we already have the data path and everything inside the data frame. So we will read from the data frame first. Now we'll create self.dataframe is equal to data frame, and self.labels is equal to torch.tensor. Now we are going to use our encoder, and it will be .fit transform, and inside the brackets we're going to put data frame of its like these brackets, and it will take class, and then we are going to make it give it a certain type of torch.long tensor, and then we are going to move it to our device, which is the GPU. Okay, great. After that, what we're going to do is we are going to read our audio path. So self.audios is equal to a list of torch.tensor for self.get. This is the part that we will add more. Spectrogram for a certain path. And we are going to write here, set it as a type. Torch.float tensor. And then we are going to write for path in our data frame file path. Okay, now what did I do here exactly? I made it a loop, okay, because we need a loop because we want to get the spectrograms of all the audio files or all the wave files that we are having. So get spectrogram function, I used get spectrogram function that we are going to implement just after a moment, and we have converted it into tensor, and the type of that tensor is a float tensor for each path inside all the paths that we are having inside the data frame. Okay, now feel free to ask any questions in the comments because I know this may seem a little bit complex, but take a while to read it. It makes sense, and hold on until we finish the whole class. It will be completed. Now we are going to have the pre-reset function len. We are going to edit this one, and we are going to return self.dataframe.shape of 0. Then we are going to write get item sorry, get item underscore underscore, and this takes self and index. Now when we start this one, it will take image path is equal to self dot data frame dot iloc. This is used to get a specific path and label with an index. Okay, so let's say you put here 2, it will get the second file path and its corresponding label. For index, 0, because this is the image path. And then for the label, we are going to get torch.tensor self.labels of index dot to device. And we are going also to write the audio. So now we got the label as well, and we are going to need the audio. So not only the path, but the audio itself, which means the audio itself by the index, okay? Which means the spectrogram file or the audio with its own features, not only the path of the audio. So we are going to write self.audios of index dot unsqueeze so that we can have a proper shape of 0 dot to device. Then we are going to return audio comma label, and we can also return the image path if we want, but we will use only these two because get item function is used. This function is automatically used with this name by PyTorch and during the training, so it will only require the inputs and the outputs. It will not require the image path, so we can always return only the inputs and the outputs. Okay, great. Now comes the interesting function, which is called get spectrogram. Now, get spectrogram is a function that that helps us get the audio features. So you know that each file we use takes usually each data we use in deep learning has its own features. For example, if we have text files, we'll see this in the next lab, but we need to convert these text files into numbers so that it can make sense to the model and we can feed it to the model. Same applies to images, and same applies to audio files as well. Audio files are the most, in my opinion, are the most like, I'll not say complicated, but tricky part. So let's see how we can implement this. So there are a lot of things in a lot of ways to extract features from audio files. In this lab, in this tutorial, we're going to get the spectrogram. So we're going to set a sample rate as 22,050. 22,050. It takes file path, by the way, okay, which is the audio path. And we're going also to set a duration, assuming that each audio file is 5 seconds, okay? We are going also to set the image height is equal to 128 and image width is equal to 256. So let's not keep so many spaces. And as I mentioned, again, you'll find this notebook on GitHub in a link attached in the description, having comments and explanations. So feel free to check it out. We will also need to load the audio file. So first of all, we will load the audio file, and librusa.load load from the file path and take the sample rate that we mentioned and duration that we mentioned. Now we read the audio file. We can use the signal directly, but it's better that we extract the spectrogram from it because it will contain more details and more data. So the spectrogram will be something like this. So something like that from Wikipedia. You can think of it as the representation of the audio file, not just a set of numbers, but it will be something like an image containing numbers. These numbers represent the image. The x-axis represents the time, and the frequency is represented by hertz or kilohertz in this case. The frequency is represented by colors, as you can see. for each specific time, it has different colors, and the color intensity represents the frequency. Okay. Now let's get back to our function. Now after we create the after we read the file, we will create the spectrogram. We will use also Librusa. It's easy, it's not an issue. And .librusa.feature dot so we have here a lot of features, as I mentioned, and we can take the MEL spectrogram. So I think, yes, that's the one. And we will use Y as our own signal, and also we will give it our sample rate, SR is equal to SR. We're going also to give it some parameters that you can play with, like this one, the FFT. And we are going also, you can have read some description of each parameter here. So these are the configurations that I found after some research on the internet that seems to be the best. Hop length is equal to 512, and number of MELs is 128. So we have got the spectrogram. Now we will need to convert it into dB or decibel, as the dB contain more details of audio files, so that it will allow the model to learn easily and find more features to learn from. So power to dB. So we are converting from power to decibel, or from the old MEL spectrogram to dB. And we are going to give it spec, and we are going also to give it np.max. Now we finally was able to get the audiophile features. What we're going to do now is to resize it. Okay, so spec resized is equal to change the size so that it can have all of them have a proper size that is matching both the duration with the sample rate. So let's see how we can do that. Librusa.util.fix length. We are going to make the length fixed for all of the data that we are having, because we need any AI model or any deep learning model needs a constant length. Okay, size is equal to duration, and duration multiplied by sample rate, and these two, let's put them inside brackets, and these are divided by 512 plus 1. This is the new size that we are having, and we are going to do one more operation, which is resize. Now we will resize that using the specs that we created with image height and image width, which are these things that we got here. And we are going also to use anti-aliasing is true. Then we will return spec resized. Let's run this. So we don't have an issue so far, but we don't have a syntax issue, but let's see if everything makes sense. So we will create a train data set is equal to custom audio data set, and it takes the data frame of train. Okay, train df, which is that one. One thing, guys, there is not a mistake, but something that we can fix here for more consistent output is that we create the label.fit transform data class. We can create this outside. Okay, so instead of creating this here, we can put it outside so that we can have all the labels here. But this will this will help us making the output more consistent. So let's do one thing. When we create the label encoder, it's better that we change inside the data set as well. So instead of having this here, we can put it before the split so that we can have a consistent output. So we can change the output before we split the data so that we can have everything set and make sense. Data underscore df for class with label encoder, and we can change this here so that we can have the class already converted into numbers or encoded into numbers before we do anything here. And here, instead of having the data of data df of class, we'll put the data frame of class, but without converting or encoding it because it's already encoded. So let's run this again, and maybe we can verify that we have a proper output. So we can only see data df here. So it's converted already. Great. Now we can proceed, and we can create here our data set, train data set and test data set, and and validation. So val, and here we're gonna put val, here we're gonna put test, we're gonna put also here test. Now let's see if everything is working fine. So if this takes few moments with you, it's okay, no problem. This is because these are audio files, and during the initialization, we are getting the specs as well. Okay, so we are getting the features of the audio file. So for each audio file, or out of this one, 4,600 and 1,000 and 1,000, for each one of them we are doing the get spectrogram function. So this is gonna take a while, so it's okay. It's not an issue. I'll continue the video when this is done. So let's give it a moment, and I'll continue the video when this is done. So we got an error here. Couldn't determine the shape of object type series. So I think we are having an issue here. So what is val? It's getting the error here in this part in labels. We are having an issue here, which is strange. So let's try to copy this one and solve this issue. Let's see what is the problem exactly. So this is val, and let's see if it's converting it or not. We are getting the error, but I'm not sure where. So val of class couldn't determine the shape of object type series. Because this is a series, not a data frame, which means that we can provide it as a list, and I think it will be solved. Yes, we should provide this as a list. So we can put this as a list here like that, and then it will work. So let's give it a few more moments to be solved. Okay, so it's done. Now let's get back to work. So we are going now to set some hyperparameters, because we are going to build the interesting part here. So the first thing we are going to set is the learning rate to 1e minus 4. Then we are going to set the batch size, which is going to be 16. And then we are going to set the epochs to 25. Okay, and I think that's enough. So we are going also to proceed train loader. We are going to create data loader so that we can iterate through the batches. Train underscore data set, and we are going to give it a batch size of our batch size. We are going also to use shuffle as true, and we are going to copy paste this for the val and the test. We're going also to write here val and here test. Great. Now the model, the part related to the model. So since we have converted it to spectrogram, and spectrogram contains somehow image structure, so we are going to build a CNN, okay, a convolution network, but it only has one channel. Okay, so the model will be a little bit big, and let's try to make things simple as much as we can. So we create a class, we'll call it net, maybe, yeah, as for network, and it inherits from NN module. Now we create, we'll create the instructor super, because it inherits. So let's write on what happened. Yeah, dot underscore init or initialize. Then we're going to define our first convolution, which is nn.conv2d. It only takes one channel as mentioned, so 1 and 16 filters. The kernel size is going to be 3 and padding is 1. Then we're going to put the second convolution layer, so nn.conv, same thing, 2d, takes 16 channels, because it will give us here, the output will be 16, number of input channels and the number of output channels. Okay, so this is the number of output channels, excuse me for any confusion. Then this will give us 32 channels, and it will give us the kernel size will be also 3, and we can set as well padding as 1. We are going also to get the conv3, which is conv2d, but this takes input 32 and produce 64 output channels, and the rest of the settings is the same. We're going also to have a pooling. The pooling can be only 1 because it doesn't need any shaping, so it will be max pool 2d 2 by 2. It returns the same shape, so we are going to use the same pooling for all layers. And we are going also to put a ReLU activation function. So nn.ReLU, I think yes, like that. And then we are going to write the flatten. After the convolution stuff, we will need the flatten part. So nn.flatten. Then we're going to write self.linear 1 as nn.linear. So now we are going to write the sizes of each one. So it will be 64 multiplied by 16 and multiplied by 32. And the output of the flatten will be 4096. You can try to play with these numbers, of course. These, I got them from here, the output of each layer. And already explained in previous lectures as well. So the second linear part is going to be linear 2, and this will be nn.linear. 4 takes input 4096 and gives the output smaller output, because now we want to start reducing stuff. Self.linear of 3 is equal to nn.linear for what now? For 1024, and gives us maybe 512. And self.output is equal to nn.linear for 512 input, and the output will be the length of the data underscore df of class dot unique. Now you can change this and write 12, but I prefer to write it this way, so that if you change the data set, this can update automatically. It's more professional. Now we can write also a dropout layer that we can put between our network, and n dot drop out, and set the dropout by 0.5. Great. Now we have created the layers. Now we will create the forward function. Okay, so forward, and this takes self and x. This is how, here in the forward function, we will see how the data goes inside the network, okay, or how the forward propagation happens inside the network, okay? Okay, great. Now, first of all, x is equal to self.conv1d of x. X is equal to self.pooling of x. Then we will have also the second conv. So, self.conv2d for x, and x is equal self.conv, dot pooling again of x. This is conv1 pooling, conv2 pooling, and we're going to do the same for conv1 to 3 without d. Suppose not d, this is the confusion. Okay, and then after we have done the convolution parts, then we can give it a ReLU. So x is self.ReLU for x. Then that's it. That's the convolution part. Now we will flatten our things. Sorry, our output. But before we do the flatten, we will change the view. Okay, so we will reshape the data to make it matching the flatten. X.view of x.size of 0 by -1, and then we will continue the flatten part normally, self.flatten of x, and then x equal self.linear of linear 1 of x, x equals self.drop out of x, put a drop out, then we will put another set of linear and a drop out, but the second linear, here we'll change it to the second linear, and we will have linear 1, 2, 3, so we'll put the linear 3 as well. And we then can put the output. Self.output x, and then we are going to return x. Now we have created the network, so or the network class. We have an error here, an n.module, so there is something wrong here. So I'm not sure why this is happening, but n.module. Okay, it should be capital letter, I think. Yes, that's the issue. Okay, great. Now we will create the model. So our model will be net dot to device, because as you know, and as mentioned in the previous lectures, PyTorch, you need always to make sure that you need to transfer manually everything to device. And device here, I mean the CUDA or the GPU that you have. Okay, great. That's the model. We can give it some like good looking from torch summary, import summary, and we can see our model by giving it a sample output. So model, and the output is by 128 and 256. Let's try to see the model, and here you go. The model is you can see the model here with some like good view, and I think everything is fine now. For your information, the total trainable parameters or total parameters are 138 million parameters, and the model takes around 10 megabytes for doing the inference or the forward propagation, and the total size is around 500, almost 540 megabyte. Okay, great. These information are not important to us for at this stage. We only know that it's 138 million parameters, which means it will take some time to train. So let's see what will happen. Now we will create the loss function. So it will be nn.cross entropy loss because it's a multi-class. And then we are going to create the optimizer as Adam optimizer. So model.parameters, and we are going to give it the learning rate as our learning rate that we have created, and that's it. So let's see how it will perform. Great. Now it took 4 seconds, no issues, everything seems fine. Now the interesting part, the training part, or the training loop. Now, I'm always, during this series of tutorials, I'm following the same template or the same structure of writing the code as much as I can. So, as usual, we'll create the lists, the empty lists, total loss, train. These are for plot, so we'll write plot here, and total loss validation plot. Then we will write also total accuracy train plot, and we are going to write also total accuracy validation plot. We are going to fill these lists inside the training loop, and we are going to use them later to plot the training progress and see if there is any sort of overfitting. Okay, for epoch, in epochs, or in range epochs that we have created here, 25 epochs. So for epoch in range epochs, we are going to start to create our own variables. So total accuracy train is equal to 0. Total accuracy for this epoch, I mean, total loss train is equal to 0. Total loss validation is equal to 0, and total accuracy validation is equal to 0. Okay, great. Now we are going to loop through the data inside the batch that we are having. So for each epoch, and then we are going to get through the data inside, because for each epoch we loop through the batches, and then for each batch we loop through the data. So now we loop through the data inside the batch. For inputs, comma labels in train underscore loader, outputs is equal to model of inputs, train underscore loss is equal to the loss criteria that we created. So we are going to get the loss of the model, so it's input, not inputs, and criteria. So for outputs, comma labels, so we are going to compare the output of the model with the original labels that we are having, and then we are going to calculate the loss. So total underscore loss underscore train is plus equal train underscore loss dot item. Then we are going to do the backward propagation. Backward. Now everything is same as previous labs. Then we are going to calculate the accuracy. Same way, train is torch.arg max. For outputs, comma access is 1. Equal labels dot. This should be inside the brackets. Labels.sum. Now what I'm doing here, I'll explain this again. Actually, what we are doing here is that we are getting the maximum, the torch argmax for outputs is equal to labels. So which we are getting like an array that is saying to us which labels are correct and which labels are wrong. And then dot sum between the outputs and the labels, or the outputs of the model and the labels. And then dot sum means to calculate the sum of the sum of the correct numbers. Okay, dot item to get it as an exact number. Now, what we will be doing here, after that, we will be doing total underscore accuracy underscore train is plus equal train underscore accuracy. Then we, this is to get the accuracy of the epoch, which should be improved after each epoch. Optimizer dot step, and then we are going to reset the optimizer dot 0 grad. Then we are going to do the validation. So with torch.noGrade or gradient, this is for inference or to do the validation. For inputs, we're going to do the same. For input, comma, labels in val loader, this is for validation data. We are going to have outputs is equal to model of inputs, so it's same, but the only difference is that it's on validation data. And we are going also to calculate the loss, so val loss is equal to iteration of outputs, comma, labels. And then we're going to have total loss val is plus equal val underscore loss dot item. Everything is same. The only thing is that we are not going to do the backward propagation, and we are not going to touch the optimizer during the validation part. Val underscore accuracy is equal to same thing. So, we can copy it from here for faster writing of the code, and then we can also copy this from here, but no, this is for training, so we can write here total accuracy validation is plus equal to val underscore accuracy. It's a bit confusing, so if you don't fully understand it, go to the notebook in the description, take your time reading it. You can digest it easily, but don't panic, it's very easy. And if you don't understand anything, just write in the comments what you don't understand. Now we are done with the training. We need to fill these lists, okay? So that will help us inside the plotting. So the lists are filled after each epoch, so they will be filled on the first loop level, okay? So total underscore loss underscore train plot dot append. So we are going to append here the rounded loss total underscore loss underscore train multiplied by 1000, and we're gonna round it to 4. Wait, this round should be inside. Yes, that's it. And we are going to copy paste this for validation. So instead of train, we'll write val, and here we are also going to write val. Total loss val plot, total loss, it's called validation plot. And this total loss val. Okay? And follows the same procedure. Then we are going to plot the total accuracy train dot append. This will be also round of what? Now this will be of total underscore accuracy underscore train. That's the one. Not multiplied, but it will be divided by, because we need it as a percentage. So it will be divided by train dot dataset. Train underscore dataset dot underscore length. So it will be divided by the total amount. So the total data that was classified correct divided by the total data that we are having multiplied by 1000, and this is to get the by 100 to get the percentage. Okay. And we are going to round this to 4 as well. And yeah, that's all. Now we are going to copy paste this, but for validation. So instead of train, we will write here validation. And instead of total accuracy train, it will be total accuracy val, like here, like that. Great. Now we're done. The only missing part is to put some print, okay? And we can also put time or a timer that can give us how long did the training took. But let's first write the training part. So let's write f and epoch print. This is epoch here, like that, for which epoch is it training now. And we can put slash number of epochs, or sorry, number of epochs. The train loss is how much? Now the train loss, we can put it here, round, for total underscore loss underscore train divided by 1000, or sorry, divided by 100 better. Can put this inside, divide by 100, and we will round it into only 4 digits. Okay, so we can also write the val, sorry, I think the brackets has confused, val or validation, or no, first train loss, then train accuracy. Then the train accuracy is going to be also the same here, but not that one, sorry. It will be the same as we already have it here, total accuracy train, which is that one. So it will be this part, total accuracy train for that epoch. It will be the whole part of that one. So we can copy paste it easily. And then after that, we can write the loss, the train loss, train accuracy. Then we can write the validation. Loss is going to be same like this one, but we will only write the val here, total loss train, so it will be total loss validation. And then we write a comma here. Let's make our prints organized. We will write validation accuracy, and this will be like this, but we will only change also the variable. Instead of total accuracy train, it will be total accuracy. Wait, what happened? Okay, typo. Total accuracy val, okay, and divide by validation dataset. Sorry, this should be validation divide by val dataset. That's a mistake. Okay, now that's all. We can print also a line, an extra line here, to make sure that between each epoch, or we can make it more fancy like that. So can print 30 equal signs between each epoch. And we can also put a timer to know when did the epochs started. So we can import up here time, or we can import it down, no problem. We can import time, and after we import time, we can write start time is equal to time.time, and we can start from here. And after the training is done, here print training time is, and we can write here time.time minus start time. We can put it also rounded, so we can round this to maybe 4 values, and we can put this inside brackets, and we can put here seconds. That's all. Let's see if it's going well. Let's try to run the training loop. So this is going to take a while, but let's make sure first that the first epoch is working, and then we are going to stop the video and continue when it's done. So so far, oh, okay, tuple doesn't define round method. Okay, so seems there is an issue with round. I think this should be, this is a typo, I believe. So round total loss train is, so let's see what is total loss train here. Now, total loss train is a number. And if we write this one like that, what we will get? We will get this without any problems. So something is okay. Let's copy the whole print and try to solve it here. I think there is a mistake somewhere, but I'm not sure where. So let's try to check where is the issue. So round here ends up, I think this round is having an issue. So round, okay, that's the problem. Okay, so we should put this inside, not outside. So that's the problem. Let's try to see again. Okay, I think I'm making the same issue somewhere. Here also. No, not here. Here is fine. But here in train accuracy, we should put this inside the brackets. Now it will work. No, still same issue is happening somewhere else. So validation is here, and so we have defined this bracket. The end of it is here. Yeah, I think the issue is maybe this will be solving the problem. Now let's try solving it in the back as well. It's extra tuple, so maybe that's the reason. Okay, round takes at most 2, but 3 were given. So I think we need to put these to separate these. So it seems that there is a typo. Okay, not sure where is the typo, but this is not helping. So let's try this way now. Round tuple doesn't define round method. Okay, now let's try to print it in a different way. Okay, now let's create, this is the make it epoch string. Okay, I'm debugging the issue with you guys, so bear with me please. And we can close the brackets that way, and we can create it in a separate line. So this is the first epoch. I think this way will be more organized. And the train accuracy, the validation loss, the validation accuracy, and close the string. And now we can try to print it. I think now it will give us where is the issue is exactly. Epoch string. Oh, sorry. Okay. Now the epoch is in this one. Okay, that's the problem. The issue is in this one. That's the problem. So we are going to do round for okay, that's a comma. This should be a division. Okay, and now it will work. Okay, let's better make it this way. The printing is more organized this way. And let's put the indentation and let's run again. So let's see if everything going good. Let's delete this cell because it's no longer needed. And let's see if everything is good. We can check also the utilization of the GPU RAM. So it seems good. No problems. Can increase the number of batch size if you want. And everything is good. So it started already the first epoch. And the only issue is that we need to add 1 because it's starting from epoch 0, not 1. But we can make this modification also. So let's interrupt and let's make epoch out of epoch plus 1. Oh, sorry, epoch plus 1. And let's run again. It's just for making things consistent while printing, but this is not necessary. It will not block anything. So let's see if everything is going fine. Okay, so we are in the last epoch now. The training took 500 seconds. Okay, so looks good, but we have one issue here. That the training accuracy already started high, so we have kind of high amount of epochs for 25. So I think we'll observe some overfitting but let's see. Now let's try to test the model. So we'll do the testing part, and we are almost done with this lab. So with torch.noGrad, this is going to be to have total loss test is equal 0 and total accuracy test is equal 0. Then we will have for index, comma, input, comma, and label. So input, comma, labels, in enumerate. So we're going to calculate. I don't think there is index. There is need for index here. I think that's not necessary. For in test loader. Yeah, okay. Now we are going to do prediction is equal to model of input, and then we are going to have accuracy is equal to torch.argmax of the same thing. So we can copy it easily. That's the one. But instead of having the this will be accuracy only, and that's it. Yes. Then we'll have total underscore accuracy underscore test is plus equal accuracy. We are calculating the accuracy now for each batch, and then we are adding it to the total accuracy here. So we will print, this should be outside the loop. We'll print total accuracy score is going to take the same thing we have here. This is to calculate the accuracy, but we will change some stuff here. So this will be total accuracy test, and this will be test data set, and that's all. Let's see what it will give us. Okay, so we have an issue here. Yeah, this is not outputs, this should be prediction. Sorry, that's my fault. And we have the accuracy is 93%. So you can put it in a more fancy way if you want. So we can, I think that we should put .item somewhere. I'm not sure, maybe here. No, not here, but we can fix it, but I think we can leave it for now so we don't complicate stuff. So the total accuracy score here, you can see it's 92%. So it's not bad, it's good accuracy. Let's see if we have any sort of overfitting. Still, accuracy could be good and we could have some overfitting, that's normal. I mean, if we avoid overfitting, we could get even better. But let's see if we have any overfitting first. Number of rows is 1 and number of columns is 2, because we will create a plot that is having 2 columns for validation loss and for, train validation loss, train validation accuracy, but 1 row. Both are in 1 row. And we'll put fig size is equal to 15 by 5. Great. Then we will put axis of 0. So the first plot is going to be to have dot plot. This is going to have what? It will have the total underscore loss underscore train plot. You remember this is the list we created during before the training. And we'll give it a label, and the label is going to be training loss. Then we'll have axis of 0 is also going to be plot. So we'll plot inside the same axis total underscore loss also, but for validation. And we will label it validation loss. Then we will write axis of 0. We'll set some specs for this axis as set underscore set. So we'll have some details here. Title, we will give it a title, training and validation loss over epochs. Okay. Then we will give it more details. So axis of 0, we will give it the X label and Y label. So dot set underscore x label, and the x in this case is going to be the epochs, and we're going to take this for y, and we're going to set it as the loss. Also, I think that's all, but we will write axis of 0 dot legend for this axis. Okay, now we're gonna do somehow the same for axis of 1, but for accuracy. So we'll copy paste this, and let's make this 1 for all of them. Instead of loss, it will be accuracy, and instead of loss here will be accuracy and accuracy. Here, instead of loss, we will also put accuracy, and here accuracy, and that's all. Now we will write plot.tight layout, and then we are going to see our plot. Let's see. Okay, so n cols, this should be without underscores, number of columns, and great. Now it's not very clear, so we can set some limit or dimension limit. So for axis 1, we can set limits so that it can give us like some good view. Set underscore y limit. So the y limit for accuracy should be between 0 to 100, obviously, because it's a percentage. And we can set also some limit for the loss as well. So the loss for 0 should be between 0 to 2. Let's see. Okay, no, I think we don't need for loss. I think for loss we need also better range because it's not very clear. So for loss, I think we can see here that accuracy is, for validation, accuracy is a little bit low and training accuracy is higher. So there is some sort of overfitting here, and we can see we can remove the limit for the loss because it will be easier for us. So if you can see here inside the loss that the it's not very clear, the overfitting. The overfitting is existing, but not very clear as training. So you can see inside the training that the validation accuracy is lower than the training accuracy, but not by so much. So, I mean, it's not very clear here, but still, there is some sort of overfitting that can be improved further, but it's not affecting much the model because you can see that the accuracy is 92% for the testing data, which is good. So that's all for this lab. This lab is complicated a little bit, and feel free to ask any questions in the comments. And don't forget to subscribe and like for more AI contents like this. If you have any ideas for future videos, feel free to share them in the comments as well. Thank you. Welcome back to the series of PyTorch. So in this lecture, we are going to study BERT classification. So we are going to do text classification with a pre-trained model. One of the most popular models, it's a transformer model. It's called BERT, okay? So we are going to see how we can detect sarcasm detection problem using this library, okay? So the dataset we are going to use is called news headline dataset for sarcasm detection. So let's have a look on it. It's from Kaggle, our usual website that we use to get the datasets. This is the dataset that we will be using, okay? It's old one, okay? And the dataset is having files as a JSON file. So don't worry, we are going to see how we can deal with that. So it's very easy, very straightforward. So this is a sample of the data. So it has the headline and is sarcastic, which is 0 or 1, okay? Something like this. Thirsty something scientist unveil doomsday clock for hair loss. So it looks sarcastic, okay? So that's why it's having 1. So it's a very straightforward data set, so we are not going to spend more time on that. So let's get started, okay? So first of all, we are going to install, we are going first to connect to T4, our usual environment, our usual GPU through Google Colab, okay? So let's first start by writing pip install transformers dash quite and pip install open datasets dash quite, and then we are going to our usual code for downloading the dataset, import open datasets as OD, and then we are going to write od.download, and we are going to take our dataset here, okay? So we're going to take that part, copy, and we are going to paste it here, okay? So let's see if everything is going well. Great, so it's asking for the username and password, and I think by now you should be familiar with that. So we're going to write the username and the password. So I will attach the video in the description on how to get the username and password. Feel free to watch it. Okay, so it's free, it's totally for free, there is nothing to worry about, and I will attach the video in the description, okay? Great, so now let's start by our imports, okay? So first of all, we will import PyTorch, okay? Then we will import something called torch.nn as nn. We are going also to use from torch.optim import Adam to import the optimizer. We are going also to use transformers library to get the original pre-trained model. From transformers, import auto tokenizer and auto model. We are going also to use from torch.utils.data import dataset data loader, and we are going also to import from sklearn.model selection import train test split. There's something wrong here, I don't know what. Import torch. Okay, let's see, maybe it's a delay. Great. From sklearn.metrics import accuracy score and import matplotlib.pyplot as plt. Then we are going also to import pandas as pd, import numpy as mp. We are going also to set the device as CUDA if torch.cuda.is available. So we'll check if the CUDA device is available, else we are going to use the CPU. Since we are on Google Colab environment, so we should have CUDA set for us. So we'll write available device is device. Let's run this and see that everything is going fine. So it's running, no errors, looks good, everything is there. We don't need to do any installations, and device is available as CUDA because we are connected to T4 here, okay? Great, now let's check the dataset is available here. And yes, here it is, okay? So let's start by reading our dataset. So we'll write data underscore data frame is equal to pd.read. Instead of reading CSV for CSV files, we will read JSON. So pandas is pretty straightforward in this, okay? And we are going to get the JSON file from here. So we are going to expand this one. We are supposed to see the files here, but it usually takes some like few moments. Not sure why it's a bit slow today. So let's copy this path and we're gonna see what is inside it. Okay, slash. So here it is supposed to have inside it something called sarcasm headline dataset.json. So we're gonna take it from here. Yeah, it opened now. It's a bit slow, okay, so no worries. And we are going to put a comma and then write lines equal true. Okay, great. Then we need to do the basic processing. So data underscore df dot drop na in place equal true. So we will just drop the missing values, and then we will print data underscore df dot shape, so we can see how many data we have, and data underscore df dot head. And by the way, we can add one more thing here, data underscore df dot drop something called drop duplicates, which is this one in place, so we can, from its name, we can drop the repeated or duplicated values. So let's run this and see what it gives us. Great, so after our pre-processing, we have the data as 26,708 and 3 columns. The columns are article link, headline, and is sarcastic. So of course, we will not need the article link, okay? So we can drop it, okay? So we can here drop the article link, dot drop, and open a brackets like that, and copy article link, and write comma in place equal true. Now it should be fine. Article link not found in access. Okay, because it assumes that article link is a row, but it's a column. So we need to specify that access equal 1. And we're good. Okay, by default, when you write the drop function, it drops by rows. So that's why it gave us an error. Okay, so great. Okay, now we can proceed with the next step. The next step is a very simple step. We used to do that before. So we will just split the data set to train, test, and validation. So we will write x underscore train, comma, x underscore test, comma, y underscore train, y underscore test is equal to our dir function train test split. And this function takes data df of what? So the first thing we should provide is the headline. This is the x, or the input. Second thing is the data frame that is sarcastic, the output. And the third one is something called test size. So we will split the data set by 70% training, 15 validation, 15 testing. The test size 0.3. So before we proceed, we want to convert this. Instead of pandas data frame, we'll make it as numpy array. Okay? Did we import numpy? We imported numpy. So we will change the data type of this to numpy array, because this is easily manageable and faster as well. So np.array, and we will also do the validation split again now. Okay, so we will do the validation step as follow: x underscore val, comma, x underscore test, y underscore val, y underscore test is equal to train test split, and we will write x underscore test, comma, y underscore test, because we are splitting again the testing. So the testing is 30%, we will split it to 15 validation and 15 testing. And the test, since we are splitting 30 to 15, 15, it means 50%, so 0.5. Great, now let's have a step of validation. So we will print the shape of each of them. Okay, so we will write test training size, so we can validate that our work is fine. Training size is x underscore train dot shape of 0, and okay, and we can also put another step of giving us how much percentage is this. So we can put something like, which is maybe something like round, what round of what? Round of x underscore train dot shape of 0, divide by the total size of the data frame, df dot shape of 0, multiplied, of course, by 100, and comma, and we're gonna put here percentage. Let's run this and see if it's true. If it's okay, so something is wrong with the calculation. So we are going to have this round. So you can round by 4 digits first, and then this should be okay, so the rounding part, something was wrong in the rounding part. Okay, and then we are going to copy paste this one for 4 times. So we're gonna replace this by validation, and this one by testing, and also we will replace this by x val, and this one by x test. Okay, and we are going to see that this have, let's write here rows. Okay, so this is a validation step. It's optional if you want to do it or not. So just to make sure that our work is correct. So yeah, here supposed to be x val, and here supposed to be x test. So we can print the correct values. Great. So it seems that we are good. It's out of 26,708. We have 18,600 for 70% training, 4,000 for 15%, 4,000 for another 15% for validation and testing. Great. So we are good in terms of the data. Now we will need to proceed with the model, the modeling part. Okay. So the modeling part is so simple. We are going to use a model called BERT base uncased. That's the one. Okay. So we're going to use this model using not auto model for must LM, but we are going to use the auto model function. So we are going to copy all of this, and we're going to retrieve it, but instead of model, we will call it BERT model, and we're going to learn why. Okay. And just use auto model, no need for must LM. And let's try to run this one and see. So this is a pre-trained model available on Hugging Face. It's open source model. No cost is required for that. It's a transformer model. Okay, we will not go deeper into the transformer explanation. Maybe in another video we'll do that, a detailed explanation of what is transformer model. But this model is one of the most popular and most powerful models used for tasks like text classification, masked language modeling, and other tasks. Okay, so this is we'll do another video about that, but this is free, available on Hugging Face, and developed by Google. Okay, the model is not so big. Okay, so you can see here that the model is around almost half GB. Okay, so it's not a big model. So this is helpful for us, of course. So let's see how we will use it. But this is a pre-trained model. We will configure the layers of this model, and we will, according to our problem, and we will see how this model works. Okay, similar to what we did in the exercise of the transfer learning of images, but for text. Okay, somehow similar. So let's write here class dataset, and we will create the dataset class now. Okay, very simple thing. We will not spend so much time here. You're already familiar with this part from if you are watching this playlist. So let's write first def init, the constructor, which takes self, x, comma, y, and inside here, we are going to write self.x is equal to list of tokenizer. So we are going to tokenize everything, and the tokenizer will take x, comma, max underscore length. So we will make sure that all the text is tokenized with the same length. Okay, so we'll set the maximum length as 100. We are going to set also truncation equal true, which means if there is anything more than 100, stop at 100, cut it, no problem, okay? And then we are also going to do padding equal true. This means that if you have a text that is less than 100, pad it and pad the text, which means the tokens make them continuous till 100, okay? I'm going to show you an example of these tokens, okay? And we're going also to do, instead of padding is true, it's by default will be true, but we want to specify by which length. So we're going to specify max length, okay? And return tensors is equal to PT, which is PyTorch tensors, okay? I'm going to explain more these things, okay? So don't worry if you're not understanding this, okay? And we are going to, let's make our things organized, move these dot to device. We will move these to the torch device for X in capital X. So I will loop through X and create these tokens and make them PyTorch tensors. And I will explain that, but let me finish this one first. Self.y is equal to torch.tensor of y, comma, d type is equal to torch.float32. And we're going also to do dot to device. Great. Now, what did we do here exactly? Okay, before we move to the next function. So here, let me put it this way. So imagine you have a sentence that says, maybe, hello, how are you? This is one sentence, okay? This sentence is, let's write here, this is the original sentence, okay? This sentence cannot go to the model like that. It needs to be converted to numbers. And in natural language processing, we call these numbers tokens. So it needs to be converted to tokens. We have something here in BERT called tokenizer, okay? So the tokenizer.json, this is something that we cannot display. It's a big one, but maybe we can see some things here. Let's go maybe to the middle. Yeah, something like this. The tokenizer is having a dictionary, okay? This dictionary consists of each word together with its token, its corresponding token. So each word is translated to a number. So let's say, for example, the word poppy is translated to 1722. Let's go maybe more. The word, I don't know, proof is 18907, okay? So you have to use the tokenizer of the model you are using so that this mapping is correct. So the model was trained on these words. So cocktail was converted to 18901, pots 18911, things like that, okay? So we need to convert this into tokens. So let's say tokens is something like this, okay? So tokens will be maybe, I don't know, maybe assuming just hypothetical numbers, maybe 30 this and maybe something like that, okay? These are the tokens. Great. Now we have a data set, we have a big data set, so we need to convert this into tokens. Good, we have converted them using the tokenizer and we gave it X. What are these parameters? Imagine you have a text that says, hello, how are you? Imagine you have another text that says only, I am good, which is 3 words, okay? Imagine you have another text that says, it's great, which is 2 words. So you have variety in these words, and this is not acceptable. You have to make all of them having the same length, okay? How do you do that? You do these 3 parameters, okay? So you set the maximum length to 100 tokens. So this will be 100 tokens. So meaning that this will be maybe dot zero, dot zero, dot zero, dot zero until 100, okay? We will do the same with all the sentences. So we will have only this part where the original text is there and the rest is filled by 0. If another text is longer, no problem, we are still preserving the information. If another text is shorter, if another text is longer than 100, then we have set truncation equal true, which means cut, stop at 100. We don't want more than this. If another text is having less than 100, then do padding to max length, which means like this. We will pad to max length, which means we will add more values and more numbers till we reach maximum length. And finally, we will return the value not as a list. We will return it as a tensor, a PyTorch tensor. We will move it to device. The next line is self.y is torch.tensor. So we are converting the output to tensor, to PyTorch tensor, having a float 32 type, and we are moving it to device as well. Okay, great. Now let's write def underscore len underscore underscore. This is again the same like the previous examples. Return len of self.x. All right, also def get item, and we will write here self comma index. These are same as previous. Okay, so return self.x of index comma self.y of index. These are coming from the original dataset class, and we need to replace them with what is suitable for our type, our data type, and our data set, a number of inputs and number of outputs. So the length returns the length of x, the total length of the output, of the input. Get item returns a specific item by index, the input of it and the output of it. Okay, great. Now let's continue here. Okay, so first of all, we need to convert our data sets above, the validation and testing and the training, to this format, to this data set type. Okay, great. Now we will write training underscore data is equal to data set of x underscore train comma y underscore train. Okay, okay, so then we will write validation underscore data is equal to data set of x underscore val and y underscore val. We are giving it our data set previously, that we did previously. Testing data is equal to data set of x test comma y test. Let's run and see if we have any problems. So everything looks good. We are converting our data sets. All looks good. And okay, so we got an error. Okay, so what's the error? The error is that expected torch D type or numpy array, but didn't get it. Okay, this is something in here. Okay, so in y train, x train, y train, x val, y val, x test, y test. So here it was expecting in which line? In training. So let's check here y. What is the type of y? So type, it should be numpy array if our work is good. Great. So it's a numpy array, and it's saying got numpy array expecting torch. Okay, that's a strange one. Okay, so here we have converted it to numpy array, which means that our work is fine. We are giving torch tensor. Okay, so this one's supposed to be t small, I believe. Okay, so this is a typo. Okay, so we are good. Okay, so now we will start writing our hyperparameters. Okay, 32 as a batch size. We are going also to use epochs as 10, maybe 10 will be enough, and we're going to use learning rate as 1e to power minus 4. Great, let's run this. Okay, no problems, it's just assigning values. And here we are going to write train underscore data loader. So we are going to create a data loader. Again, if you didn't watch the previous videos in the playlist, data loader is an object in PyTorch. It allows us to loop through the batch size. Okay. Okay, so we write data loader as training data, comma batch size as batch size, comma shuffle equal true. We can shuffle and we can ignore the shuffling. Shuffling means changing the order of the data randomly to avoid biasing. So we can leave it, no problem. And we will just change this to val data loader, or maybe validation. Let's be better, and testing. And here we will also write validation data, and here we are also going to write testing data. Okay, let's run. Great, we are good. Now let's build our model. Okay, first of all, we will build the model like we used to build it inside in the previous videos. Okay, no problem. Define my model, and we will write here nn.module. We will create, sorry, this is not defined, this is a class. Should be like that, yeah. Inside this class, we'll create our instructor. The instructor will be self, comma, BERT, and then down we will write super, my model, self, everything like we did before, okay? Underscore, underscore, init, brackets. Great. Then we will create self.BERT is equal BERT, our original BERT model, okay? We will create also a dropout layer. So we'll write dropout is equal to nn.dropout 0.25, the dropout value. And we'll create self.linear 1 is equal to nn.linear for 768,384. Sorry, forgot the brackets. Okay, and I'll explain that, don't worry. Self.linear 2 is equal to nn.linear 384,1, because this is binary classification, and self.sigmoid, so we can get proper output, is equal to nn.sigmoid. Great. We'll define forward function. The forward function takes self, comma, input IDs, comma, attention mask. We'll write pooled output is equal to self dot BERT. I'll explain that, don't worry. Input ID, just write with me. Attention mask, comma, return underscore dictionary is false, and we'll write of 0, we'll write 0. Okay, like that. And then output is equal to self.linear 1 for the pooled output, and then output is equal to self.dropout for output, and output is equal to self.linear 2 for output, and finally output is equal self.sigmoid for output, and return output. Great. Run. No syntax error, no problems. Great. Now what did we do here? First of all, this is a class for the model BERT. Okay, this model, we will receive BERT model, the original BERT model, which we have defined here, which we have got here. Where is it? Here, BERT underscore model. So we will give it as an input, and then we will create a couple of layers. Dropout, I think you are already familiar with that, but why did we choose 768? BERT model, the default size of BERT model, outputs 768. These 768 are a representation for the text. Okay, so this text, meaning that this text is represented by 768 values, a vector of 768. Okay, so we will take this 768 and we will give it to the linear layer that we have added. This linear will output half of this size, which is 384. Then another linear layer which will output 1. Okay, so we added 2 layers, or actually 3 layers, including the dropout, where these layers will make the classification part for us. Okay, and finally the self.sigmoid. Okay, great. Now in the forward function, we got the output from BERT, and this output we gave it to linear 1, then dropout, then linear 2, then sigmoid, as we explained here with these sizes. Okay, okay, great, sounds good. Now let's do the next step now. Okay, we'll write for param in BERT underscore, we will first, yes, BERT underscore model dot parameters, and we will write here param dot requires grad is false, and then we will create our model. Okay, so we call it only model now. My model for BERT underscore model, and again .to device. Let's run, and it's working fine. So what did we do here? We took our model, we made sure that the model functions, the model layers, the original model layer, it's a pre-trained model, okay, don't forget that, which means that the model is already having knowledge. We want to preserve this knowledge. We only want to change in the linear 1 and linear 2, the layers we have added, okay, not the original layers of the model. This will be faster and of course more accurate because the model is already pre-trained. Okay, great. And we set it to false, which means don't train the parameters of BERT model. And now next we created our model, which we gave it BERT model, this one, and this one now is having the full architecture that we wanted. So my model, you will see now that my model, only model, it's called only model. So you will see now that the model contains everything we want. It contains the BERT part, and it contains also our part. So drop out linear 1, linear 2. Okay, great. So we are good to go. Okay, now if we proceed, we will just first, before we start writing the training loop, we will create the loss function. So since this is a binary classification, we'll create it as BCE loss, binary cross entropy, and we'll create optimizer as Adam. And this optimizer take the model.parameters. These are the parameters that our optimizer will optimize. And learning rate as LR, which is 1 e to power minus 4. Let's run, make sure everything is fine. Great, all looks good. Now, next step is a simple one. Not a simple one, but let's say you are already used to it because this is what we did, the same training loop that we did. So let's start by writing total loss train plot is equal to this list, total accuracy validation plot is equal to empty list. We are going also to write total accuracy train plot. Let's make it consistent. Total loss train plot, total loss validation plot, and total accuracy train plot, and total accuracy val, or maybe let's write it better, validation plot is equal also an empty list. So we'll write for epoch in epochs in range epochs. These lists, again, as a recap, are to store the loss for each epoch and visualize it at the end to see if there is any overfitting. Great. So we are going to write total underscore accuracy underscore train is 0, which will be accumulated through every epoch, through every batch. Total underscore loss underscore train is also 0. total underscore accuracy underscore val is 0, and total underscore loss underscore val is also 0. Okay, now we will go inside the batch for index comma data in enumerate train underscore data loader. Okay, and here we are going to get the inputs comma labels as data, and we are going to move them to device. That's an extra validation step to make sure that they are moved to device. Okay, and then we are going to run these examples into the model. Prediction is model of inputs of input underscore IDs, because BERT produced two things, the input IDs and something called attention mask. Okay, and this one we write dot squeeze of 1, and then we will write inputs of attention mask, which will also produce dot squeeze of 1, and finally dot squeeze of 1. Okay, so we have set dot squeeze, same reason as previous videos, where we make sure that the batch size is involved here. Okay, so it outputs in terms of batch, not only in terms of one item to be loaded. Okay, we write batch loss is equal to what? Is equal to the loss function we created, and it takes prediction because of course in the beginning the model will output crap, so we need to make sure that we calculate the loss or the error, and we will total loss train, we will see how much loss we got inside this batch, so we will add it to the previous 0 here, and we will add batch loss dot item. Great, and then accuracy is equal to, we will see what accuracy we got, so we will write prediction dot round, so we can get our prediction is equal label, so we see if it's equal to the label, which means if they are equal, dot sum, so we can see how many values are equal to each other, and dot item to extract the number. So we will see how many values in terms of accuracy are similar to each other, the model that predicted them. Then with this accuracy, of course, we'll do same as loss, so total accuracy train is plus equal to accuracy, and then we will do the backward propagation, so batch loss dot backward, and then optimizer dot step, so we will allow our optimizer to modify the weights, and then optimizer resetting, which is optimizer dot 0 grad, and that's all. Now validation with torch.no grad, which means with torch.no gradient, which means no training. Now we will only do a validation to see the progress of our model. We again will go into another loop for index comma data in enumerate what? Enumerate validation data loader, because we are trying now on validation in. Okay, and now we will start doing the same. So the same things, everything is same, and we will calculate the loss and accuracy, but we will not. So we're gonna copy these. We will not take the optimizer and the backward propagation because we are only checking the validation now. Okay, same, but don't forget to change these things. So total accuracy validation instead of total accuracy train, and instead of total loss train, it's going to be total loss validation. This one. Okay, so total loss validation, total accuracy validation. Great. Did we miss anything? I don't think so. Great. Now after all of that, we need to insert inside the list our values, okay, so that we can plot at the end. So we will write total underscore loss underscore train underscore plot dot append. We will append what? We will append round, so total underscore loss underscore train. We will make sure it's divided by 1000 so we can get reasonable values, and split by 4. Okay, now we are going to do the same with the total loss for validation, but instead of loss train here, we will write loss val. Okay, so total loss val, I think it's called total loss validation plot, not val plot. Okay, and then we are going to do something similar in accuracy. So total underscore accuracy underscore train underscore plot dot append. Okay, and we're going to do round for total underscore accuracy underscore train, and we're going to check out of the total amount of data, okay, which of the total amount of data of the training, okay, which is divide by training underscore data dot underscore underscore len underscore underscore brackets, which we have created above, okay, the len function, you remember this one, which gives us the total number of the rows inside the training data. Okay, and after we do this, okay, we will need to put all of these inside brackets, because at the end we will multiply it by 100 to get a percentage, and we will round this by 4. Okay, great. Now we are going to do exactly same but for validation. Okay, so now you know the way, so we will just copy paste it, and we will just change the things here. Sorry, not accuracy. We will just change the val here, and don't forget, of course, to make sure that this is validation data. Okay, now we will need something beautiful to print, okay, something to know the progress of the training. So we will write here 3 quotes, and we will leave a line like this, and we will write f here to inject string inside the print, to inject the variable inside the string, and we will write epoch number, and we will write curly brackets like this, and we will put epoch +1, so we make sure we don't start from 0. And this is just for our display, okay, so it's nothing really, you know, difficult here. You can do this as you like. Okay, train loss is also curly brackets, and we'll write total underscore loss underscore train divide by 1000, which is this one basically, so we can copy it, paste it directly, and we will write train accuracy as this one. Okay, around for the accuracy, where is the accuracy? Train plot, this is the one. So we're going to take it all like this, put it inside curly brackets. The next line, for simplicity, we will put the same, so validation underscore loss, and we will take this from the total loss validation, which is this one, so we can print and visualize the things happening, and accuracy loss, sorry, validation loss, validation accuracy, is confusion, sorry for the confusion, validation accuracy, and we can put just indentation here so they can be on the same level. And validation accuracy, we are going also to put same things, the thing we have appended here in the list, total accuracy validation plot, which is this one. Great, we are ready for the training, so we can start the training and see how it performs. Great, label is not defined. Okay, so we have here, I think it's labels, not label, and I believe here also supposed to be labels. Okay, let's run again. It's a simple thing, no problem. Okay, another one is label also. So here it's supposed to be labels, and here it's supposed to be labels. Okay, so int plus equal for int is not something that's not working here. plus equal accuracy. So, okay, are we getting the item? Okay, so we should be getting the item with the brackets. So let's see if everything is working fine. And okay, so no news is good news. I think we are going good. We have set it to 10 epochs. Okay, you can try more if you want, but 10 epochs I think is enough for this problem, and especially that we have a limited runtime in Google Colab. So I think 10 epochs will give us some good results. Let's see. If everything is printing fine, at least the first epoch is printed fine, I will stop the video and we are going to continue after the training is done, so I don't waste your time, okay? So let's see that everything is going fine. Great. I think nothing means that everything is good. So it's stopping here. Okay, so anyway, I'll stop the video now and we can continue after the training is done. Okay, so our model is still training. We are not yet done. But I just want to check with you the CPU utilization. Sorry, the GPU utilization. So we're using only 0.9 of 15 GB RAM because BERT is a very small model. So it's fine. We are not utilizing everything we have. You can see here that the train accuracy started 80. So it started already high because you remember it's a pre-trained model. And it got increased and reached 86%. Okay. And validation accuracy was 85 and it was reaching 87, then 84. So there is a sort of overfitting here. Of course, you can play with the hyperparameters, you can increase the epochs, you can try more things, and maybe you can see different results, okay? Now let's wait for the final epoch. We are now at the validation step. You can see the green line here. We are at the validation step of the final epoch, yeah. And we are expecting to finish this soon. So until this is done, we can start writing the code of the testing. Okay, it's done. So it reached 87 of training and 87 validation. So maybe this epoch only was something wrong with it. But anyway, let's start with writing the test code to see the final accuracy. So torch.nograd, same code as previous, and we'll write total loss test is equal to 0, and we'll write total accuracy test is equal to also 0, and we will write for index comma data in enumerate, same but for testing loader, data loader, okay. And we write inputs, comma labels, same, everything is same, is equal to data. In fact, we can copy the things from here. Yeah, better, and this will save us some time. So we will just change the total accuracy test to here, and we will put also total loss test here. And we are going to print the accuracy score. So accuracy score on testing data is, we will put here F, and we're going to write again same thing as we were writing here. So this is to calculate the accuracy, so we're going to take this copy, just doing it the quick way, guys, so that we can have these things done quickly. Total accuracy test divide by testing data, and I think that's all. So let's try to run and see. This is percentage, of course, and let's check this out. So the total accuracy is going to be printed shortly. Let's give it a moment. Okay, now the only missing part is the plotting. Okay, this is optional, but of course this is to observe the overfitting. Accuracy score on testing data is 84.6%, which is good. Not the best, but it's good. Can be improved further, of course. We can increase the epochs. We can try playing a bit with the hyperparameters so we can get better results. But so far, I think it's good, 84.6%. Okay? Great. So remember that we ran it only on 10 epochs, so we can give it more, but this is enough for now, okay? Because here we have some limitations. Let's create a figure and its axis. So plt.subplots. So we create two plots. So number of rows it's equal to 1 and number of columns is equal to 2, and we are going to have fig size equal to 15 by 5. Axis of 0, we are going to write axis of 0 dot plot total of loss train plot, comma, label is equal to training loss. And we're going also to write axis of 0. We will give it some details, so we'll plot on it also the total underscore loss underscore validation underscore plot, comma, label is equal to validation loss. Okay, we are going also to write axis of 0 dot set title, so we'll set the title of the chart. The title of the chart, sorry, going to be training underscore, sorry, training and validation loss over epochs. And then axis of 0 dot set x label, so in this case the x will be the epochs, and we're going to set the y label, change this to y, and we'll write here as loss. Okay, and we will enable the legend. Then we're going to do pretty much the same, but with slight changes, but for the axis of 1. So maybe we can put it, I think I can select multiple here. Yeah, this axis of 1. And we're going to write here, instead of loss, we're going to write ACC for accuracy, ACC for accuracy. And we'll write here accuracy, and we'll write here also accuracy, and we'll write accuracy here. So this will be accuracy. Great. Finally, we need to do one thing. We want to set the limit of axis 1 dot accuracy limit is between 0 to 100. Okay, so we will set here to 0 to 100, and we are going also to set the axis here to some limitations, starting from 0 to 1. So we can have a graph that is, you know, neat and looking good. Tight layout, and then we will write plot.show. So let's run and see our beautiful plot here. So okay, so it's supposed to be n rows, not number of rows, I think n columns. Okay, so we got an error, ylim is not there, so it should be set y limit and set y limit. Okay, so we are good here. Okay, so you can see that actually in accuracy we cannot see we cannot see overfitting. In loss there is a slight overfitting. Still, again, we can improve the model. But I think that's all for this exercise for today. If you have any questions, feel free to write in the comments. I'll check the questions. And also please note that I will attach in the description the GitHub repo that contains all the PyTorch tutorials. This is the last tutorial for this playlist. Feel free to enjoy and to have a look on the channel. You will find other videos, and I will try to upload more videos as well. And again, everything in this tutorial was used open source, so you don't need to pay anything. All you need is your laptop. You don't need even resources or powerful resources. We are using a free cloud service from Google Colab. And yeah, that's all. Make sure that you disconnect the runtime and That's all. Thank you very much for watching, and I hope you enjoy this playlist.